explain the sharp edges seen in the nebula and the apparent lack of chaotic acts. The central star in an advanced state approach to a wolf nearing its final collapse. The material ejected into space could be part of a larger process in which layers of stellar atmosphere are shed over time, forming structured nebulae that persist long after the original outburst. The exact mechanism behind the symmetry remains a topic of ongoing study, with hypotheses ranging from episodic eruptions caused by internal instability to a controlled expansion influenced by a strong toroidal magnetic field. Spectroscopic analysis reveals that the nebula is rich in both silicate and carbon-based dust, suggesting complex chemical interactions occurring within its expanding shell. The presence of ionized hydrogen and oxygen lines indicates exposure to intense ultraviolet radiation, which is slowly altering the composition of the surrounding medium. These processes are crucial in enriching the interstellar environment with heavy elements that to the four generations of starry system. The suggest has been thousands, though whether it has remained stable over time or if it has undergone significant changes in structure. Some researchers propose that the formation is an optical illusion, where a more cylindrical or bipolar outflow appears squared due to our viewing angle. Others argue that external influences, such as a dense interstellar medium or remnant stellar winds, may be reinforcing the shape by constraining material along specific planes. Advanced telescopes equipped with high-resolution spectrographs are expected to provide more precise data on the velocity distribution of gas and dust. By analyzing how light interacts with different regions, astronomers hope to reconstruct the three-dimensional shape and determine whether the observed symmetry is an inherent property or a temporary phase. If the central star is approaching a supernova event, its surrounding nebula could dramatically brighten as the explosion interacts with the ejected material, similar to what has been observed in other massive star systems. Structured nebulae suggest that mass loss in massive stars follows patterns that are more than previously thought. Planetary nebulae often display systems due to the expansion of dying stars. The object exhibits a level of precision than conventional models. If stars are indeed playing a dominant role, suggests that similar structures could remain under their orientation or distance from Earth. Infrared observations have also hinted at the presence of complex organic molecules within the nebula, which could have formed through photochemical reactions triggered by high-energy radiation. Such environments are thought to be crucial in the early stages of planetary system development, as they contribute to the formation of prebiotic compounds that later become part of interstellar dust clouds. Understanding how these materials evolve in different stellar environments provides insight into the chemical diversity of the galaxy. Future research will focus on mapping the precise movement of gas within the nebula and determining whether external factors are influencing its evolution. If a binary companion is confirmed, it could provide further evidence that multiple star systems are a key factor in shaping structured nebulae. Long-term monitoring may reveal subtle shifts in brightness or morphology, indicating ongoing dynamic processes that have yet to be fully understood. If the central star eventually undergoes a supernova, it could transform the surrounding region by sending shockwaves through the nebula, triggering secondary reactions and possibly altering its structure. The resulting supernova remnant would provide valuable data on how pre-existing mass loss affects the aftermath of stellar explosions. If a neutron star or black hole forms at the core, it may interact with the surrounding material in ways that produce additional high-energy emissions, making it a potential source of radio waves or X-ray bursts. The precision of the formation continues to challenge existing astrophysical models, suggesting that either previously unknown mechanisms are at work or that magnetic shaping plays a far greater role in stellar evolution than currently assumed. Upcoming telescopes with adaptive optics and interferometry will provide deeper insights into the processes governing the expansion of ionized gas and the interaction between radiation and dust within the nebula. While its ultimate fate remains uncertain, its significance as an astrophysical case study is undeniable. Whether it is a short-lived phase of stellar evolution or a long-standing feature that will persist for thousands of years, it represents a rare and valuable opportunity to study the forces that shape the most massive stars in the cosmos. The answers it holds could refine our understanding of how stars evolve, how they lose mass, and how they influence the galactic environment over cosmic timescales. The forces responsible for shaping this nebula remain a subject of debate, with multiple mechanisms potentially working in tandem to maintain its strikingly structured form. The presence of a dense circumstellar medium suggests that earlier mass ejection events may have interacted with surrounding material, creating shock fronts that reinforced the observed geometry. If stellar winds or episodic eruptions from the central star were directed by an unseen companion, their effects could have compounded over time, gradually sculpting the nebula into its current configuration. Magnetic fields are another possible factor influencing its development. In some high-energy astrophysical environments, magnetic pressure can guide ionized gas along preferred paths, constraining outflows into collimated jets or symmetric lobes. If this phenomenon is occurring here, it could help explain the sharp definition of the nebula's edges and the near-identical structure on opposite sides of the central star. Observations of other massive stellar remnants have shown that even weak magnetic fields can have a profound impact on outflow dynamics, reinforcing the idea that this nebula's shape may be magnetically driven. The chemical complexity of the surrounding gas adds another layer of intrigue. The discovery of molecular hydrogen and polycyclic aromatic hydrocarbons within the nebula suggests that the region has undergone prolonged exposure to ultraviolet radiation, leading to chemical reactions that produce complex organic compounds. If this material later becomes part of interstellar clouds, it could contribute to the formation of planets or even prebiotic chemistry in future stellar systems. This highlights the role of evolved stars not only as sources of heavy elements but also as potential contributors to the early chemistry of planetary environments. The velocity distribution of ejected material is also a critical factor in understanding the formation of the nebula. If the gas is expanding uniformly, it would suggest that the star has been losing mass gradually over an extended period. However, if velocity gradients are detected, with some regions moving faster than others, it could indicate episodic bursts of energy, possibly linked to a hidden binary companion or internal stellar instability. High-resolution spectroscopic studies will help determine whether the structure has remained stable or if it is actively evolving, with changes in brightness or morphology providing additional clues. Comparisons to other known stellar outflows provide valuable context for interpreting this structure. The similarity to bipolar planetary nebulae, which are often shaped by binary interactions, suggests that the nebula may represent an earlier stage of this process in a much more massive system. If future observations confirm the presence of an orbiting companion, it could provide strong evidence that binarity is a key factor in the formation of highly structured nebulae, challenging existing models of single-star mass loss. The possibility that the central star is approaching a terminal supernova phase adds an additional layer of urgency to ongoing research. If this is a pre-supernova system, then the surrounding nebula may play a crucial role in determining the characteristics of the eventual explosion. A dense circumstellar medium could shape the supernova's light curve, producing an extended afterglow or even influencing the type of remnant that forms. If the core collapse results in a neutron star or a black hole, the interaction between the compact object and the surrounding nebula could generate secondary emissions, including high-energy X-ray or radio bursts. Some researchers propose that this nebula represents a previously unrecognized category of structured stellar outflows, distinct from both planetary nebulae and classical supernova remnants. If so, it could mean that highly organized mass loss occurs in more stars than currently expected but remains undetected in systems with less favorable viewing angles. Advanced three-dimensional modeling, combined with data from next-generation telescopes, will be necessary to determine whether similar formations exist elsewhere in the galaxy. Long-term monitoring will be essential to track any changes in the nebula's structure. If subtle shifts in brightness or gas distribution are detected, it could indicate ongoing mass loss or dynamic interactions within the expanding material. Alternatively, if the nebula remains unchanged over decades of observation, it would suggest that its formation was driven by a past event rather than active processes occurring in the present. Either scenario will provide valuable insights into how massive stars shed their outer layers and how those layers evolve over time. The nebula's role in the broader astrophysical landscape extends beyond its immediate surroundings. If it is indeed an example of a structured pre-supernova outflow, it could help refine predictions for other massive stars nearing the end of their life cycles. Understanding the processes shaping this formation could improve models of how supernovae interact with their environments, potentially leading to better interpretations of historical supernova remnants observed throughout the galaxy. Future research will focus on uncovering the underlying drivers of the nebula's symmetry, whether they be magnetic forces, binary interactions, or unknown stellar dynamics. Upcoming missions and observational campaigns will provide increasingly detailed data, helping to answer fundamental questions about the role of evolved stars in shaping the structure of the interstellar medium. Regardless of what mechanisms are ultimately responsible, the nebula remains a rare and invaluable opportunity to study the complex interplay between stellar evolution, mass loss, and the physical forces that govern the cosmos. As observational techniques continue to improve, new details about this enigmatic formation will likely emerge, shedding light on the precise mechanisms responsible for its near-perfect symmetry. The role of radiation pressure in shaping the expanding gas is an area of active investigation, as intense stellar winds could be driving material outward along well-defined paths. If the star is emitting energy anisotropically, with stronger radiation in specific directions, it could be influencing the way ejected material disperses into space. This could help explain the structured nature of the nebula, particularly if interactions with a surrounding dust disk or magnetic field are reinforcing its geometric appearance. High-energy phenomena may also be contributing to the evolution of this structure. Some researchers suggest that the presence of shock fronts, regions where fast-moving gas collides with slower material, could be shaping the expanding nebula. These interactions create areas of increased density and ionization, altering how light scatters and giving the nebula its distinctive brightness distribution. If these shocks are being driven by periodic stellar outbursts, then the formation could be the result of multiple ejection events over time, each adding to the overall complexity of its structure. Infrared observations continue to provide new insights into the dust and gas composition of the surrounding environment. Data suggests that the dust grains within the nebula are relatively large compared to those found in diffuse interstellar clouds, possibly indicating that they have undergone significant processing due to radiation collisions. If this region is rich in carbon-based compounds, it could support the idea that evolved stars contribute not only to heavy element enrichment but also to the formation of molecular precursors essential for planetary system development. Determining the precise age of the nebula is another critical aspect of ongoing research. By analyzing the expansion velocity of different gas layers, astronomers aim to estimate when the initial mass ejection occurred. If the nebula is relatively young, it could be the result of a recent instability in the central star, whereas an older formation would suggest a more gradual mass loss process over an extended period. This distinction is important in understanding whether this structure is a transient phase that will evolve into a more diffuse remnant or if it represents a long-lived phenomenon sustained by continuous energy input. The potential presence of a binary companion remains a crucial question, as its confirmation would provide a strong explanation for the nebula's ordered structure. If a secondary star is orbiting the central object, its gravitational influence could be directing material into specific flow patterns, producing the observed symmetry. Some models suggest that if a white dwarf, neutron star, or even a black hole is present, accretion-driven outflows could be responsible for the formation's striking shape. Identifying subtle variations in the motion of the primary star or detecting indirect signs of a hidden companion through X-ray or radio emissions may help resolve this mystery. Further study of the polarization of light from the nebula will be useful in determining whether magnetic forces are playing a significant role in its evolution. If light scattering patterns indicate the presence of aligned dust grains, it could suggest that a strong magnetic field is guiding the expansion of gas. Such a scenario would align with models of magnetically collimated outflows, which have been observed in other astrophysical environments, including young stellar objects and active galactic nuclei. One of the most intriguing possibilities is that this formation represents an early stage of a process that has not been widely documented in astrophysics. If it turns out to be a precursor to a more well-known structure, such as a planetary nebula or a supernova remnant, it could provide a unique opportunity to study how these phenomena develop over time. Observing how the nebula changes in the coming years will be crucial in determining its future trajectory, whether it will eventually dissipate into the interstellar medium or continue evolving into a more complex structure. If the central star ultimately undergoes a supernova, the surrounding material could play a key role in shaping the explosion's observable characteristics. The presence of dense circumstellar matter could cause significant interaction between the supernova shockwave and the pre-existing nebula, leading to an unusually bright and prolonged event. If this occurs, it could offer direct observational evidence of how mass loss influences the final stages of massive star evolution. Long-term monitoring with next-generation telescopes will be essential in answering the remaining questions surrounding this extraordinary structure. Instruments capable of resolving fine details in the gas distribution, magnetic field orientation, and spectral properties will provide the data needed to construct a more complete picture of its origins and evolution. If similar objects are identified elsewhere in the galaxy, it may indicate that these types of structured outflows are more common than currently believed, potentially leading to a re-evaluation of existing models of stellar mass loss. Regardless of its ultimate fate, this nebula remains one of the most visually striking and scientifically valuable examples of how complex forces interact in the late stages of stellar evolution. Whether shaped by binary dynamics, magnetic fields, episodic outbursts, or a combination of multiple factors, its existence challenges conventional astrophysical theories and offers an unparalleled opportunity to study the intricate processes governing massive stars. Future observations will undoubtedly bring new discoveries, deepening our understanding of how these cosmic structures form, persist, and eventually transform into the next generation of celestial phenomena. As observations continue to refine our understanding of this extraordinary formation, the interplay between multiple astrophysical forces becomes increasingly apparent. The near-perfect symmetry suggests that a finely tuned combination of stellar winds, radiation pressure, gravitational dynamics, and possibly magnetic confinement is at work. Each of these factors contributes to shaping the expanding shell of gas and dust, maintaining its structural integrity over time. Whether this level of organization is an inherent property of certain types of stellar outflows or a rare coincidence of conditions remains an open question. Infrared spectroscopy has revealed variations in the temperature and density of different regions within the nebula, indicating that it is not a uniform shell but rather a complex, layered structure. This suggests that multiple ejection events may have occurred at different times, each adding a new component to the overall formation. If past eruptions have been episodic, possibly regulated by internal instabilities in the central star or interactions with an orbiting companion, the nebula could be an evolving record of its progenitor's mass loss history. The detection of specific ionized elements in the surrounding gas suggests that high-energy radiation from the central star is actively altering its chemical composition. Regions exposed to the most intense ultraviolet and X-ray flux exhibit signs of ionization-driven molecular dissociation, while more shielded areas retain heavier molecules and dust grains. This dynamic environment provides insights into how massive stars influence their surroundings, gradually enriching the interstellar medium with elements forged in their interiors. One of the primary challenges in understanding the nature of this structure is determining whether its symmetry is a transient feature or a long-term characteristic. If it is the result of a recent outburst, it may slowly degrade over time as the expanding material interacts with external forces. On the other hand, if it is stabilized by ongoing processes, such as a sustained mass flow or a persistent magnetic field, its geometry may remain largely unchanged for thousands of years. Tracking subtle shifts in the nebula's brightness and morphology over successive observational periods will be essential in distinguishing between these possibilities. Comparisons to other known examples of structured nebulae suggest that ordered mass ejections are more common than previously assumed. However, the degree of symmetry observed here is exceptionally rare, indicating that specific conditions must be met for such formations to arise. If future surveys identify similar objects in different regions of the galaxy, it could provide a broader statistical foundation for understanding how often these structures occur and what factors contribute to their development. Advanced numerical simulations are being used to model the potential formation scenarios for this system. By incorporating variables such as stellar rotation, pulsation-driven mass loss, and binary interactions, researchers hope to replicate the observed structure and determine which forces dominate its evolution. Early results suggest that a combination of rapid stellar rotation and a companion's gravitational influence could create flow patterns that resemble the nebula's distinct shape. If these models prove accurate, they could offer a new perspective on the role of binarity in shaping circumstellar environments. Another intriguing aspect is the potential for future variability in the central star itself. If it is nearing the end of its evolutionary cycle, further instability may lead to additional mass ejections or luminosity fluctuations. Such changes could provide direct observational evidence of how the formation is being influenced by ongoing stellar processes. If a sudden brightening event occurs, it could be a sign of an impending transformation, possibly signaling the transition into a Wolf-Rayet phase or even the approach of a terminal explosion. If the star ultimately undergoes a core collapse supernova, the surrounding nebula could play a critical role in shaping the aftermath. A dense pre-existing medium could result in an unusually energetic explosion, with shock waves producing intricate interaction patterns within the already structured outflows. Such an event would be a rare opportunity to observe how massive stars influence their own supernova environments, offering insights into the processes that govern the final stages of stellar life. Long-term monitoring efforts will focus on detecting changes in expansion velocity, ionization levels, and thermal emissions within the nebula. Any deviations from the expected behavior could indicate previously unknown influences at work, potentially revealing new physics governing stellar outflows. With upcoming space-based and ground-based observatories providing increasingly detailed data, a clearer picture of this remarkable formation will continue to emerge. Whether this structure is an exceptional case or part of a broader, yet underappreciated category of organized mass ejections, its study is reshaping perspectives on how stars interact with their surroundings. The precise forces maintaining its near-perfect symmetry remain one of the most compelling mysteries in modern astrophysics, and future discoveries may provide the missing pieces needed to unlock its true nature. Regardless of what new revelations come to light, this nebula stands as a striking testament to the complex and often unexpected beauty of stellar evolution. The persistence of such a structured formation raises fundamental questions about the longevity of ordered nebulae and the mechanisms that sustain their geometry over time. If the observed symmetry is not merely a transient effect, then ongoing processes must be actively maintaining its precise form. One possibility is that the radiation pressure from the central star is continually shaping the expanding gas, reinforcing existing structures and preventing dissipation. In this case, variations in stellar output could lead to subtle but measurable shifts in the nebula's morphology, offering insights into how radiation-driven mass loss influences circumstellar environments. The presence of complex molecular compounds within the expanding shell suggests that chemical evolution is occurring on a large scale. As ultraviolet and X-ray radiation interacts with dust and gas, it triggers photodissociation processes that break apart existing molecules and encourage the formation of new ones. This cycle of destruction and recombination is key to understanding how massive stars contribute to the molecular diversity of interstellar space. If the conditions within the nebula are stable enough, they may support the gradual synthesis of increasingly complex compounds, further enriching the surrounding medium. Velocity mapping of the nebula's outflows is another avenue of investigation that may yield crucial insights into its formation history. If different layers of gas are expanding at distinct rates, it could suggest multiple episodes of mass ejection, each contributing to the overall structure. By reconstructing the motion of individual gas clouds within the nebula, astronomers can determine whether the expansion is accelerating, slowing down, or maintaining a steady rate. A uniform velocity distribution would support the idea of a single, well-coordinated outflow event, while irregularities could indicate ongoing dynamic interactions between different layers of material. The role of external influences, such as interactions with the surrounding interstellar medium, is also worth exploring. If the expanding nebula is encountering regions of higher density gas, it could be experiencing external pressure that helps define its shape. This scenario is particularly intriguing because it would imply that the large-scale structure of the interstellar medium plays an active role in shaping stellar remnants. If such interactions are confirmed, they could offer a broader context for understanding how similar nebulae form across different galactic environments. Advances in computational astrophysics are enabling the development of increasingly sophisticated simulations that attempt to recreate the conditions necessary for such a structured formation. These models incorporate factors such as stellar rotation, magnetic field dynamics, radiation transport, and binary gravitational effects. The goal is to determine whether a single dominant force is responsible for shaping the nebula or if multiple factors are working together in a complex interplay. Early results suggest that while radiation pressure and magnetic fields alone can produce organized outflows, the addition of a binary companion significantly enhances the likelihood of maintaining long-term symmetry. If a compact object is present within the system, it could further complicate the dynamics of the nebula. A neutron star or black hole companion could be influencing the surrounding material through accretion-driven winds or relativistic jets. These high-energy processes could create additional structure within the nebula, potentially explaining regions of enhanced brightness or density variations observed in different wavelengths. If future observations detect X-ray emissions or rapid fluctuations in radio signals, it may provide direct evidence of a compact remnant playing an active role in the system. Another aspect of interest is whether this nebula represents a unique evolutionary path or if it shares characteristics with other known structures that have been observed at different stages of development. If similar formations exist but have gone unnoticed due to unfavorable viewing angles, it could suggest that such ordered mass ejections are more common than previously thought. A systematic survey of structured nebulae using high-resolution telescopes could help identify additional examples, refining our understanding of the conditions necessary for their formation. The long-term future of the nebula remains uncertain, as its fate will largely depend on the evolution of its central star. If the star continues shedding mass at a steady rate, the surrounding structure may gradually expand and fade over thousands of years, blending into the interstellar medium. Alternatively, if the star undergoes a more dramatic transition, such as collapsing into a white dwarf, neutron star, or black hole, it could leave behind a compact remnant that continues to interact with the surrounding material. If this leads to periodic bursts of energy, the nebula may experience episodic reillumination, creating a variable emission profile that persists long after the initial mass ejection event. If a supernova does occur within the nebula, it could produce one of the most visually and scientifically interesting explosion remnants ever observed. The pre-existing structure would shape the way the supernova shockwave propagates, creating intricate patterns of glowing filaments and ionized gas. The resulting explosion could provide valuable data on how mass loss before core collapse affects the properties of the supernova itself, offering a real-world test case for theoretical models of stellar death. Regardless of its ultimate fate, this nebula remains an astrophysical anomaly that continues to challenge conventional understanding. Its striking symmetry, dynamic environment, and potential connection to high-energy astrophysical processes make it an ideal subject for continued study. The combination of observational data, theoretical modeling, and future technological advancements promises to unlock further insights into the mechanisms responsible for shaping such extraordinary cosmic structures. In the broader context of stellar evolution, this nebula highlights the diversity of pathways that massive stars can take as they approach the end of their life cycles. Whether it represents a transient phenomenon or a more persistent stage of mass loss, it serves as a reminder that the processes governing the formation and evolution of stellar remnants are more intricate than previously assumed. As research continues, each new discovery will bring us closer to understanding the fundamental forces that sculpt the universe's most fascinating and mysterious celestial objects. As more data is gathered, the intricate dynamics governing this structured outflow become clearer, yet many aspects remain elusive. The balance between stellar wind pressure, radiation forces, and gravitational interactions is delicate, and minor fluctuations in any of these variables could significantly alter the nebula's morphology over time. If its current shape is maintained for an extended period, it would suggest an ongoing regulating mechanism, possibly a combination of persistent mass loss cycles and external constraints imposed by either a magnetic field or a binary companion. A deeper understanding of the internal motion of the gas is crucial in deciphering whether the structure is static or evolving. If gas and dust are flowing outward at a uniform velocity, then the nebula is expanding symmetrically without significant turbulence. However, if regions within the outflow exhibit differences in acceleration, it may indicate that multiple processes are acting simultaneously. The presence of high-velocity streams, for example, could point to localized shock waves where ejected material interacts with remnants of previous stellar mass loss. If the star at the center is rotating rapidly, it could also be affecting the mass ejection pattern. Fast rotation alters the shape of the stellar atmosphere, making it more oblate and enhancing equatorial mass loss through centrifugal forces. This would naturally produce an extended disk or toroidal structure around the star, which could act as a guiding framework for the broader nebula. If rotation is a key factor, then future spectroscopic studies of the star's surface may reveal Doppler broadening effects, indicating differential velocity regions across its surface. The role of ionization fronts within the nebula is another aspect of interest. If the central star's radiation is continuously exciting the surrounding gas, it may be forming stratified layers where different elements are ionized at varying depths. This would lead to a multi-tiered composition where hydrogen, helium, oxygen, and heavier elements are distributed according to their ionization potentials. Understanding these ionization boundaries could provide insight into how far the star's influence extends and whether the outer regions of the nebula are still actively shaped by radiation or are merely residual structures from past eruptions. The possible presence of dust filaments or molecular clouds within the nebula suggests that complex interactions between gas phase elements and solid particles are occurring. Dust grains play an important role in astrophysical chemistry, acting as catalysts for molecule formation by providing surfaces where atomic interactions can take place more efficiently. If the nebula is rich in carbonaceous or silicate dust, it may indicate that material from the star is condensing into solid form, eventually contributing to the raw material for future planetary system formation. One key observational goal is to determine whether the nebula is optically thick or if it allows significant amounts of radiation to escape. If it is largely transparent at certain wavelengths, then light from the central star may be escaping in directed beams, influencing surrounding interstellar clouds beyond the immediate boundaries of the structure. This could result in faint emission regions detectable in infrared or radio wavelengths, providing clues about how the nebula interacts with the broader galactic environment. The possibility of a faint, extended halo surrounding the main structure is also being explored. Some nebulae exhibit diffuse outer layers, where lower density gas gradually transitions into the surrounding medium. If this system follows a similar pattern, then it may have an extended outer envelope that is not immediately visible in current observations but could be revealed through deep exposure imaging techniques. If such a halo is present, it may contain older material from earlier mass ejections, offering a more complete picture of the star's long-term evolution. Further study of light polarization within the nebula may also help in determining whether magnetic fields are contributing to its structure. If dust grains are aligned along a preferred axis, it could indicate that an underlying magnetic field is shaping the flow of ionized gas. Strong magnetic confinement could explain why material appears to be expanding in a highly organized manner rather than dissipating irregularly, as is typical in many other stellar outflows. High-resolution radio observations could provide additional evidence of magnetic influence by detecting synchrotron radiation, which occurs when charged particles spiral along magnetic field lines. The long-term monitoring of the nebula's brightness and shape will provide important clues about its future evolution. If no significant changes are observed over the coming decades, it could suggest that the system has reached a stable equilibrium, where forces acting within it counterbalance one another. However, if gradual shifts in emission intensity or structural features are detected, it may indicate that the nebula is still undergoing active reshaping, driven either by continued mass loss or external forces acting on the expanding shell. If the central star eventually transitions into a late-stage degenerate remnant, such as a white dwarf or neutron star, its interactions with the nebula may take on new characteristics. A cooling white dwarf would emit lower energy radiation, potentially altering the ionization structure of the nebula over time. If a neutron star or black hole forms, accretion of remaining material could generate episodic bursts of high-energy emissions, further complicating the evolutionary trajectory of the surrounding gas. With the advent of more sensitive astronomical instruments, including future space-based and ground-based telescopes, finer details of the nebula's composition and kinematics will become accessible. Multi-wavelength campaigns combining optical, infrared, radio, and X-ray data will allow researchers to construct an increasingly refined model of the processes governing this remarkable structure. By extending observational coverage to different regions of the electromagnetic spectrum, new physical interactions may be revealed, providing additional pieces to the puzzle of its formation and persistence. Understanding this nebula has broader implications beyond its immediate structure. If similar objects are discovered in different star-forming regions or near other evolved stellar systems, it could indicate that such formations represent a recurring phase in the life cycles of massive stars. This would provide new constraints on theories of stellar mass loss and the role of binarity, magnetic fields, and radiation pressure in shaping astrophysical outflows. Each discovery would bring us closer to understanding the universal principles that govern the transformation of stars and the lasting impact they leave on their environments. As research continues, the nebula remains a fascinating subject at the intersection of multiple astrophysical disciplines. Its structured appearance challenges traditional models, suggesting that either previously unrecognized mechanisms are at work or that known processes are operating in a more complex manner than currently understood. The insights gained from this system will not only refine our understanding of mass loss in evolved stars but may also influence broader concepts in astrophysics, from supernova progenitors to the formation of chemically enriched regions within galaxies. No matter what future observations reveal, this nebula stands as a striking testament to the intricate and often unexpected interactions that shape the cosmos. The persistence of such an intricate and symmetrical structure suggests that it is not merely a fleeting phase but a system governed by sustained forces. If the nebula were purely the result of a single explosive event, its features would have begun to dissipate in a more chaotic fashion over time. Instead, the defined edges and organized outflows indicate that ongoing mechanisms are reinforcing its structure, preventing it from dissolving into an irregular cloud. Understanding the nature of these stabilizing forces will provide crucial insights into how long such formations can persist and what role they play in the broader galactic ecosystem. One of the key aspects under investigation is whether the gas and dust within the nebula are interacting with interstellar magnetic fields beyond the immediate influence of the central star. If so, the entire system may be embedded within a larger-scale magnetized region that is influencing the way material is distributed. This would mean that its shape is not solely the result of internal stellar processes but is also being conditioned by environmental factors on a much larger scale. The interaction of expanding nebulae with the ambient galactic magnetic field is a relatively unexplored area of research, but it could have profound implications for understanding the formation of structured outflows in other astrophysical settings. The possibility that the nebula is part of a larger feedback loop within its local stellar neighborhood is another avenue of study. If mass loss from the central star is feeding surrounding molecular clouds, it could be triggering secondary star formation in nearby regions. In this scenario, the nebula is not just a byproduct of stellar evolution but an active participant in the recycling of matter, enriching the interstellar medium with heavier elements and influencing the next generation of star formation. If observations detect enhanced star-forming activity in adjacent regions, it would support the idea that evolved stars contribute more directly to galactic chemical evolution than previously assumed. Infrared imaging continues to reveal variations in dust grain size and composition, suggesting that material within the nebula is undergoing active processing. Some regions appear to contain larger, more complex carbonaceous compounds, possibly formed through prolonged exposure to ultraviolet radiation. If dust grains within the nebula have been altered by repeated ionization cycles, they may exhibit unique spectral signatures that could serve as a marker for similar objects elsewhere in the galaxy. By identifying the specific types of molecules present, researchers may be able to determine whether this environment is conducive to the formation of organic precursors to planetary systems. The thermal structure of the nebula is another critical factor in assessing its long-term stability. If the gas within it is being heated unevenly, localized instabilities may form, leading to subtle structural changes over time. High-resolution temperature maps created from multi-wavelength observations could reveal whether certain regions are cooling more rapidly than others, potentially setting the stage for future condensation of material. If dense clumps are forming within the nebula, they could eventually collapse under their own gravity, leading to the formation of new stellar objects. While this would be an unexpected outcome for a system of this type, it cannot yet be ruled out. The search for variability in the brightness of the central star remains ongoing. If the star exhibits periodic fluctuations in luminosity, it may indicate pulsational instabilities affecting its outer layers. These variations could, in turn, influence the mass loss rate, leading to episodic enhancements in the nebula's structure. If brightness changes are detected, correlating them with observed changes in the nebula's emission patterns could help establish a direct link between stellar activity and the evolution of the surrounding material. The outermost layers of the nebula are of particular interest, as they may provide a record of its earliest formation stages. If weak shock waves are detected propagating through the outer edges, it could suggest that the nebula is still expanding into previously undisturbed interstellar space. These shocks could be producing low-density filaments that are difficult to detect in optical wavelengths but may be revealed through radio observations. If such features are confirmed, they would provide valuable clues about the nebula's expansion dynamics and whether it is still actively interacting with its environment. One of the most significant remaining uncertainties is whether this structure represents a phase that other massive stars undergo or if it is an exceptional case. If similar objects exist but have not yet been identified, it could mean that such nebulae are more common than previously thought but remain undetected due to observational limitations. Systematic searches using next-generation telescopes with enhanced sensitivity in the infrared and radio bands may reveal whether this is part of a broader class of stellar outflows that have gone largely unrecognized. If the nebula is indeed a precursor to a supernova event, its surrounding structure may serve as a unique observational target when the explosion occurs. The interaction between the supernova shockwave and the pre-existing circumstellar material could produce intricate patterns of emission, allowing astronomers to witness the complex interplay of stellar remnants and nebular evolution in real time. The ability to study such an event would provide unprecedented insights into how mass loss influences the properties of supernova explosions, helping to refine models of core collapse dynamics. The continuing refinement of astrophysical models incorporating observational data from this nebula will lead to a better understanding of the forces shaping high-mass stellar environments. As computational capabilities advance, simulations will be able to incorporate increasingly detailed physical parameters, allowing researchers to test different formation scenarios and compare them directly to observational data. If a definitive explanation for the nebula's structure emerges, it will not only resolve one of the most intriguing astrophysical mysteries but also provide a framework for understanding similar objects that may be discovered in the future. Regardless of what new findings emerge, this nebula remains a compelling example of the complexity of stellar evolution and the diversity of structures that can arise from seemingly chaotic processes. Its continued study will provide valuable insights into how stars interact with their surroundings, how mass is redistributed throughout the galaxy, and how the final stages of stellar evolution shape the interstellar medium. Each new observation brings us closer to uncovering the full story behind this remarkable formation, revealing the intricate and often unexpected ways in which stars leave their mark on the cosmos. As research progresses, the long-term evolution of this nebula remains one of the most compelling unknowns. Whether its structure will remain stable for thousands of years or gradually dissipate into the surrounding interstellar medium is still unclear. If the forces maintaining its symmetry weaken over time, the well-defined edges may begin to blur as expanding gas disperses. However, if there are persistent shaping mechanisms, such as ongoing stellar mass loss, magnetic field interactions, or external pressure from surrounding interstellar clouds, the structure may remain largely intact for an extended period. Observations in multiple wavelengths continue to refine our understanding of the nebula's internal structure. Radio observations, for instance, are particularly useful in detecting cold gas components that may not be visible in optical or infrared light. If significant amounts of molecular gas are present, it could indicate that the outer layers of the nebula are cooling and condensing, which might lead to the formation of secondary features such as filamentary streams or localized high-density regions. These structures, if confirmed, would provide further evidence of ongoing interactions between stellar ejecta and the surrounding environment. The distribution of heavier elements within the nebula is also of interest. If enriched materials such as oxygen, nitrogen, and carbon are concentrated in specific regions, it could suggest that different layers of gas are expanding at different rates or that localized ionization fronts are influencing chemical processes. Detailed spectral analysis may reveal whether these elements were produced in earlier nuclear fusion cycles within the central star or if they are the result of more recent nucleosynthesis in an unstable stellar atmosphere. Another crucial factor in understanding the nebula's evolution is determining whether it is interacting with external gas flows from other nearby stellar sources. If the region around the nebula contains additional massive stars that are shedding material, their outflows could be influencing the expansion and shape of the structure. This would suggest that nebular symmetry is not solely dictated by the properties of the central star but is also affected by its galactic environment. If such interactions are detected, they could provide new insights into how massive stars shape their surroundings on a larger scale. The question of whether the central star is truly alone remains unresolved. The possibility of an unseen binary companion continues to be explored through precise radial velocity measurements and high-resolution imaging. If a compact object, such as a neutron star or white dwarf, is orbiting within the system, its gravitational effects could be contributing to the organized shape of the surrounding material. A binary scenario could also explain periodic mass ejection events, which would be consistent with the layered appearance of some regions within the nebula. The alignment of the structure with potential galactic magnetic fields is another factor under examination. If the nebula's shape is influenced by larger-scale magnetic interactions, it would suggest that it is not an isolated phenomenon but part of a broader network of interconnected astrophysical processes. If future measurements detect signs of external magnetic influence, it may support the idea that structured stellar outflows are not solely dictated by internal dynamics but can be modified by extrinsic forces acting on a galactic scale. If this nebula does eventually undergo a transformation due to a supernova explosion, the resulting remnant could provide a rare opportunity to observe how a pre-existing structured outflow interacts with a high-energy shock wave. Such an event would likely produce an asymmetric supernova remnant, with expanding material encountering dense regions in some directions while escaping more freely in others. This would create a highly complex emission pattern, providing valuable data on how circumstellar matter influences the outcome of core collapse events. Even if a supernova does not occur in the near future, the nebula's gradual evolution will offer important insights into how mass loss continues in late-stage stellar systems. Long-term observations will track changes in its brightness, expansion rate, and spectral properties, revealing whether the structure is gradually dispersing or if it remains dynamically active. If the nebula continues to exhibit stability over time, it may challenge existing theories of mass ejection and suggest that previously unrecognized stabilizing mechanisms are at work. Future telescopes, particularly those designed for high-resolution spectroscopy and polarization studies, will be instrumental in unraveling the finer details of the nebula's composition and motion. By studying variations in emission across different regions, astronomers may be able to determine whether specific forces, such as localized shock waves or radiation pressure differences, are influencing its evolution. These observations will help build a more comprehensive model of how massive stellar outflows develop and persist. This nebula remains a remarkable case study for astrophysics, not only because of its striking appearance but because of the numerous unanswered questions surrounding its origin, stability, and eventual fate. Whether it represents a rare phenomenon or an overlooked stage in stellar evolution, it challenges conventional assumptions and invites further exploration into the complexities of massive star systems. Each new observation brings us closer to a full understanding of the forces shaping the cosmos, demonstrating that even in an era of advanced astronomical technology, the universe continues to reveal mysteries that push the boundaries of human knowledge. As the study of this structured nebula advances, its significance extends beyond its immediate formation, hinting at broader astrophysical processes that govern the life cycles of massive stars. The long-term stability of its shape suggests that mass ejection is occurring in a controlled manner, possibly influenced by a combination of radiation pressure, rotational effects, and external constraints imposed by a larger galactic framework. The degree to which these forces interact remains an open question, but each new observational dataset refines our understanding of the mechanisms at play. Recent spectroscopic measurements have revealed variations in ionization levels across different regions of the nebula, suggesting that the central star's radiation is not evenly distributed. This could indicate that the star is experiencing rotationally modulated emissions, where different parts of its surface emit varying intensities of ultraviolet and X-ray radiation over time. If so, the asymmetry in radiation output could be influencing the density distribution of surrounding gas, reinforcing the structured shape by preferentially ionizing certain areas while leaving others relatively undisturbed. The search for a binary companion remains an ongoing effort, with continued radial velocity studies and high-resolution imaging campaigns aiming to detect any subtle gravitational influences that might suggest the presence of an orbiting secondary object. If a compact remnant, such as a neutron star or a white dwarf, is hidden within the system, it could be driving periodic outflows through mass transfer interactions. Even if no direct evidence of a secondary star is found, the possibility of past interactions with a now-merged companion remains a plausible explanation for the structured ejection pattern. Magnetohydrodynamic modeling suggests that if magnetic fields are present within the nebula, they could be acting as a stabilizing force, guiding ionized plasma along specific paths and preventing the structure from dispersing chaotically. If confirmed, this would provide new insights into how large-scale magnetic configurations contribute to the formation of highly organized stellar remnants. Future polarization studies will be crucial in determining whether aligned dust grains or synchrotron emission signatures indicate the presence of magnetic shaping. The discovery of molecular compounds in specific regions of the nebula provides further evidence of ongoing chemical evolution. The identification of carbon-rich molecules, possibly including complex organics such as polycyclic aromatic hydrocarbons, suggests that the nebula is not simply a passive stellar remnant but a dynamic chemical environment where high-energy radiation is continuously altering molecular structures. This has implications for the study of interstellar medium enrichment, as such nebulae may act as sources of prebiotic material that eventually contribute to the formation of planetary systems. Another aspect under examination is the thermal structure of the gas and dust within the nebula. If temperature gradients are detected, it could indicate localized heating effects caused by shocks or regions where high-energy radiation is penetrating deeper into the expanding layers. By mapping these temperature variations across different spectral bands, astronomers can better understand whether the nebula is undergoing a steady cooling process or if certain regions are being repeatedly reheated by external influences. Long-term monitoring efforts aim to determine whether the nebula exhibits subtle changes over time. If small-scale shifts in brightness or morphology are detected, they could signal ongoing interactions with external gas clouds or internal stellar variability influencing the surrounding material. If, on the other hand, the structure remains largely unchanged for decades, it would imply that the forces maintaining its shape are remarkably stable, challenging traditional models of nebular evolution. The broader implications of this research extend to the study of massive star populations in different galactic environments. If similar structured nebulae are discovered elsewhere, it would suggest that this is not an isolated phenomenon but rather a recurring phase in the late-stage evolution of certain types of stars. Systematic surveys using next-generation telescopes could reveal whether other examples exist, providing statistical evidence to support new theoretical frameworks. If this nebula eventually transitions into a supernova remnant, it will provide a unique opportunity to observe how a structured circumstellar medium interacts with an energetic explosion. The resulting supernova shockwave would propagate through the pre-existing outflows, creating intricate emission patterns and potentially leading to asymmetric expansion dynamics. Such an event would be invaluable for refining models of core-collapse supernovae and their interactions with surrounding material. Regardless of its future trajectory, this nebula remains one of the most fascinating astrophysical puzzles of recent times. Its highly ordered structure defies conventional expectations, prompting a re-evaluation of the processes governing stellar mass loss and outflow organization. Whether shaped primarily by binary interactions, magnetic confinement, radiation-driven winds, or a combination of multiple forces, it offers an unparalleled opportunity to study the interplay between stellar evolution and nebular dynamics. The continued investigation of this system will contribute to a deeper understanding of the fundamental principles that shape celestial structures, from the smallest dust grains to the largest-scale galactic formations. Each discovery adds another layer of complexity to our understanding of the cosmos, demonstrating that even in an era of advanced observational capabilities, nature continues to surprise and challenge our theoretical frameworks. The nebula remains a beacon of scientific curiosity, inviting further exploration into the hidden mechanisms that govern the life and death of stars across the universe. As research into this remarkable nebula advances, it continues to serve as a key astrophysical laboratory, revealing the interplay of multiple forces that govern the evolution of massive stars. Its near-perfect symmetry, long-term stability, and complex chemical composition challenge traditional models of stellar mass loss and nebular dynamics. While most nebulae form through chaotic processes, this structure suggests a level of organization that is difficult to explain through standard mechanisms alone. The persistence of its shape implies that self-regulating forces must be at work, reinforcing its geometry over time and preventing it from dissipating into an amorphous cloud. One of the most intriguing aspects of this system is its potential connection to broader astrophysical phenomena. If the nebula is shaped by a previously unknown feedback mechanism, it could offer insights into how large-scale magnetic fields, binary interactions, and stellar wind collisions contribute to nebular evolution. Some researchers propose that if the star is rotating at high speeds, the centrifugal forces could be influencing the way material is expelled, leading to an anisotropic outflow pattern. This could explain why mass ejections appear to be funneled along specific axes rather than expanding spherically, as is common in many evolved stellar systems. Infrared studies have revealed that the dust composition within the nebula is not uniform, with certain regions showing enhanced concentrations of complex molecules. This suggests that the nebula is not only a passive structure but an active site of chemical evolution, where high-energy radiation is triggering reactions that modify the molecular landscape over time. The detection of carbon-based compounds, including large polycyclic aromatic hydrocarbons, PAHs, hints at a potential connection between nebular environments and the formation of prebiotic molecules in space. If the conditions within the nebula resemble those found in protoplanetary disks, it could provide clues about the earliest stages of planetary system formation and how organic material is distributed across the galaxy. Another avenue of investigation involves mapping the expansion rate of the nebula's outer layers. If the velocity of the gas varies across different regions, it could suggest that multiple mass ejection events occurred at different times, each contributing to the layered structure. By analyzing Doppler shifts in the spectral lines of ionized gas, astronomers can reconstruct the three-dimensional motion of material within the nebula, determining whether it is undergoing uniform expansion or if internal forces are modifying its trajectory. If deviations from standard expansion models are detected, it could provide evidence for ongoing interactions with an unseen companion or an external pressure source shaping the outflow. The possibility that the nebula is part of a larger-scale galactic structure is also being explored. If the surrounding region contains other remnants of past stellar activity, it could indicate that the system is embedded within a dense stellar cluster, where multiple massive stars have contributed to shaping the environment. In this case, the nebula may not be an isolated formation but part of a network of interconnected astrophysical processes, where interactions between different stellar outflows have created complex patterns of gas and dust. Detecting such connections could provide valuable insights into how massive stars collectively influence the structure of their host galaxies, contributing to the enrichment of interstellar space with heavier elements and driving the formation of new stars. Another critical question is whether the nebula is in a stable or transitional phase. If it remains unchanged over long periods, it would suggest that the forces shaping it are self-sustaining, maintaining its geometry over extended timescales. However, if subtle shifts in brightness or morphology are observed, it could indicate that the nebula is evolving dynamically, either through continued interactions with its central star or through gradual dispersion into the interstellar medium. Monitoring these changes over time will help determine whether the nebula is a long-lived phenomenon or if it represents a fleeting stage in the late evolution of its progenitor. If a supernova were to occur within the nebula, it would provide an unprecedented opportunity to study how an explosion propagates through a highly structured circumstellar medium. Unlike typical supernova remnants, which often expand into relatively diffuse environments, this system would present a complex pre-existing structure that could dramatically influence the resulting shockwave dynamics. The interaction between the explosion and the nebula could lead to asymmetric ejecta patterns, unusual light curves, or the formation of intricate filamentary structures as ionized gas collides with denser regions of dust. If such an event were to be observed in real time, it would offer invaluable data on how massive stars end their lives and how their surrounding environments shape the final stages of their evolution. The presence of strong magnetic fields within the nebula remains an open question, but if confirmed, it could provide a crucial missing piece in explaining its structure. If the expelled gas is interacting with an external magnetized region, it could be following field lines that dictate its movement and alignment. High-resolution polarization studies will be essential in determining whether the observed symmetry is the result of magnetic confinement, offering new insights into how large-scale cosmic magnetic fields influence nebular dynamics. The future of research into this nebula will involve deeper investigations into its chemical composition, velocity distribution, and interactions with its surrounding environment. Advanced instruments such as the James Webb Space Telescope, JWST, Extremely Large Telescope, ELT, and Atacama Large Millimeter/Submillimeter Array, ALMA, will allow astronomers to probe deeper into its molecular and atomic structure, revealing details that were previously beyond the reach of observational technology. By combining data from multiple wavelengths, from radio to X-ray, researchers will be able to construct a comprehensive model of the nebula's evolution, identifying the forces responsible for its formation and predicting its long-term fate. This nebula remains one of the most extraordinary examples of how stellar mass loss can create highly ordered structures in space. Whether its symmetry is the result of binary dynamics, magnetic shaping, radiation pressure, or a combination of these factors, its existence challenges conventional theories of how stars interact with their surroundings. If it is part of a broader class of structured nebulae that have yet to be fully recognized, it could lead to a revision of current models of stellar evolution, highlighting previously unaccounted for processes that influence the final stages of a star's life. Regardless of what future discoveries reveal, this nebula stands as a striking example of the complexity of astrophysical systems. It demonstrates that even in an era of highly advanced astronomical technology, nature continues to present puzzles that defy easy explanation. Its study will not only deepen our understanding of individual stellar outflows but also contribute to a broader perspective on how stars shape the galaxies they inhabit. Each new observation brings us one step closer to unraveling the mysteries of this extraordinary formation, reinforcing the idea that the cosmos is far more intricate and dynamic than we ever imagined. As our understanding of this enigmatic nebula deepens, it becomes increasingly clear that its significance extends beyond a single remarkable formation. It is a testament to the intricate forces governing stellar evolution, challenging existing theories and prompting new questions about how massive stars interact with their surroundings. Whether its structure is the result of binary interactions, magnetic shaping, radiation-driven winds, or an interplay of multiple forces, it represents a rare and invaluable case study in astrophysics. The future of research into this system will rely on a combination of observational and theoretical advancements. With the next generation of telescopes, including the James Webb Space Telescope, JWST, the Extremely Large Telescope, ELT, the Square Kilometre Array, SKA, and future X-ray observatories, astronomers will be able to probe deeper into the nebula's chemical composition, velocity distribution, and potential magnetic fields. High-resolution polarization studies will determine whether external magnetic influences are shaping its structure, while multi-wavelength spectroscopy will refine our understanding of its thermal dynamics and molecular complexity. If variations in brightness, expansion rates, or ionization levels are detected over time, they could provide key evidence of ongoing interactions within the system. Another avenue of exploration lies in the search for similar objects elsewhere in the galaxy. If other nebulae with comparable symmetry and structure are discovered, it could indicate that this is not a unique anomaly but part of a broader, yet previously unrecognized class of stellar outflows. Systematic surveys using deep-field imaging techniques may uncover additional examples, helping to establish the conditions necessary for such formations to occur. If no other similar structures are found, it will reinforce the exceptional nature of this nebula, making it a priority for continued study. Long-term monitoring will also be essential in determining the nebula's ultimate fate. If it remains stable over centuries, it would suggest that the forces maintaining its shape are self-sustaining, potentially revealing new physics governing mass loss in evolved stars. However, if it begins to change, whether through gradual dissipation, interaction with the interstellar medium, or the influence of an external shockwave, it may provide a rare opportunity to witness a transitionary phase in the evolution of a stellar remnant. If a supernova event occurs within this structure, the resulting shockwave could interact with the pre-existing nebula in a way that has never been observed before, offering unprecedented insights into how massive stars shape their surroundings both before and after their explosive deaths. Ultimately, this nebula serves as a reminder that even in an age of advanced astronomical instrumentation and sophisticated theoretical models, the universe still holds mysteries that defy easy explanation. It is a challenge to our understanding of stellar physics, a catalyst for new discoveries, and a window into the complex and dynamic processes that shape the cosmos. As technology advances and new data become available, each observation brings us closer to unlocking the full story behind this extraordinary formation, ensuring that its legacy will endure as one of the most intriguing astrophysical puzzles of our time. Whether it remains a stable, structured beacon in the cosmos or transforms dramatically in the coming centuries, its study will continue to inspire curiosity, push the boundaries of astrophysical research, and expand our knowledge of the fundamental forces that govern the universe. This galactic giant is not a static entity, it is part of the eternal cycle of cosmic evolution. The universe is not a still canvas but a dynamic space where galaxies are born, develop, interact, and ultimately change or fade away. Right now, this spiral system is in an active phase of star formation. Its arms are illuminated by young, massive stars, but astrophysical models predict that this period will not last forever. Over time, the processes regulating the birth of new stars will lead to a gradual decline in this activity. Star formation cannot continue indefinitely. The supply of cold gas, the raw material for new stars, will eventually be depleted. Cosmic winds and stellar explosions will expel much of this material into intergalactic space. The activity of the central black hole may also play a role, heating the surrounding gas and preventing it from collapsing into new stars. If no fresh gas flows in, the system will gradually enter a passive state where star birth ceases. The black hole at the galaxy's core is a key factor in determining its future. If it continues to consume matter, it may become even more active, releasing powerful jets of energy and creating shockwaves that alter the surrounding space. Such processes can either stimulate star formation or suppress it. If the surrounding gas is exhausted, the black hole will enter a dormant state, leaving behind only faint traces of X-ray radiation. This system does not exist in isolation. Nearby galaxies orbit around it, and there is a possibility that they will collide in the future. A merger could trigger a burst of star formation, but it could also destroy the ordered structure of the spiral arms, transforming the system into an elliptical form. Such events often lead to chaos in the internal dynamics of stellar orbits and fundamental changes in morphology. If this formation becomes part of a larger galactic cluster, the pressure from the surrounding environment may strip it of its remaining gas, completely shutting down star formation. In that case, it will become a fainter and more passive system where stars age without new generations replacing them. Observations suggest that this stellar island is surrounded by a vast dark matter halo. This invisible substance holds the galaxy together, preventing its stars from drifting apart. The question of how dark matter is distributed and what properties it possesses remains one of the greatest mysteries in modern astrophysics. Some theories suggest that dark matter consists of dense clumps, influencing the motion of stars and gas. Other hypotheses propose that dark matter interacts with itself in ways that we have yet to detect. Over time, the galaxy will become dominated by stars that have reached the end of their life cycles. White dwarfs, neutron stars, and black holes will gradually replace the younger, more luminous stars. If star formation ceases entirely, this world will, in trillions of years, become a place populated only by the faint remnants of once bright celestial bodies. Beyond internal factors, the system's fate will also be shaped by the evolution of the universe itself. The expansion of space is gradually increasing the distances between galaxies. If this process continues, then in the far future, surrounding objects may disappear beyond the cosmic event horizon, leaving this stellar world in complete isolation. The question of whether this galaxy could ever become home to intelligent life remains unanswered. If life arises within one of its planetary systems, it will encounter conditions different from those found in our own galaxy. In an era when bright stars fade, civilizations may search for ways to harness the energy of white dwarfs, neutron stars, or even black holes. Perhaps, in the distant future, advanced technologies will emerge that allow civilizations to manage energy resources on a galactic scale. This stellar world is one of countless objects in the universe, each a dynamic system evolving over time. Its fate could take many paths, retaining its current structure, transforming into an elliptical system, merging with other formations, or becoming isolated due to the expansion of the universe. But no matter what its final destiny may be, it remains part of the continuous cosmic process. Every star, every gas cloud, every gravitational force is a link in the great chain of the universe's evolution. We have only begun to uncover this story, and many discoveries still lie ahead. As observers continue to study distant galaxies, each new detail becomes part of an endless exploration that will never truly end. As time passes, this vast galactic structure will continue to change, shaped by both internal and external cosmic forces. While the present era is marked by active star formation, powerful stellar winds, and dynamic interactions, the distant future will bring a more gradual transformation. The balance between creation and destruction, between the birth of new stars and the fading of the old, will ultimately determine how this system evolves over billions or even trillions of years. The slow depletion of gas will lead to a decline in the birth of bright, massive stars. The spiral arms, once vibrant with nebulae and young stellar clusters, will begin to fade as fewer new stars form to replace those that die. The remaining gas will become increasingly diffuse, spread thinly across the galaxy, no longer able to collapse into dense clouds that fuel star formation. If no external gas flows in from intergalactic space, this system will slowly transition into a quieter, less active state. While the visible structure of the galaxy undergoes these changes, its invisible dark matter halo will continue to play a crucial role in its long-term evolution. The unseen gravitational framework that holds the stars and gas together may influence future mergers, interactions, and even the galaxy's eventual fate. Some theories suggest that dark matter halos are not static but may evolve over time, possibly affecting how galaxies like this one maintain their structure over cosmic timescales. As the number of new stars decreases, the population of stellar remnants will grow. White dwarfs will become the dominant stellar type, their faint glow persisting as they gradually cool over trillions of years. Neutron stars and black holes will also become more common, remnants of the most massive stars that once illuminated the galaxy. If enough black holes exist within the system, they may begin to interact gravitationally, forming dense clusters or even merging into larger structures that could eventually fall toward the central supermassive black hole. Over billions of years, the galaxy may undergo a transformation driven by gravitational interactions with other systems. If it merges with a neighboring galaxy, it may lose its spiral structure, becoming an elliptical system where stars move in more randomized orbits. Such a transition would mark a major shift in its evolutionary path, reshaping the way stars and stellar remnants are distributed throughout its volume. In a more extreme scenario, if the galaxy is absorbed into a massive galactic cluster, it may experience what is known as ram pressure stripping. This process occurs when a galaxy moves through the hot gas that fills the space between galaxies in a cluster. The pressure exerted by this intergalactic medium can strip away any remaining gas, effectively halting star formation entirely. This would leave behind a system composed mostly of aging stars, gradually fading over time. Beyond these local events, the larger-scale evolution of the universe itself will influence the ultimate fate of this galactic giant. The expansion of space, driven by dark energy, is accelerating. If this acceleration continues indefinitely, galaxies will become increasingly isolated, drifting apart until they can no longer interact with one another. Over time, this system may find itself alone in an expanding void, with no nearby galaxies left to merge with or draw gas from. In the far future, as the last remaining stars exhaust their nuclear fuel, the galaxy will enter its final stage. White dwarfs will continue to cool, becoming black dwarfs, cold, dark remnants emitting no light. Black holes will persist, slowly evaporating through Hawking radiation, though this process takes an unimaginably long time. Over an almost inconceivable timescale, the galaxy itself may become a vast, dark collection of degenerate matter, silent and unchanging. But even in this distant future, the story of this galaxy will not truly be over. The fundamental forces that shaped it, gravity, dark matter, cosmic expansion, will continue to operate. New discoveries may one day reveal unknown processes that influence its fate in ways we cannot yet predict. Perhaps advanced civilizations, if they arise and endure, will find ways to manipulate stellar remnants, harnessing the energy of neutron stars or even black holes to sustain life long after ordinary stars have burned out. For now, this galaxy remains a vibrant and active system, a luminous beacon in the cosmos. Its arms swirl with gas and dust, its stars shine brightly, and its core harbors the powerful force of a supermassive black hole. It is a system still in motion, still evolving, still participating in the grand, ongoing story of the universe. And as we continue to observe it, to study its mysteries and map its future, we are reminded that the universe itself is not static. Every galaxy, every star, every atom is part of an endless cosmic dance, a process of change and transformation that spans across time and space. This galaxy's story is far from over. It is just one chapter in the ever-unfolding narrative of the cosmos, a reminder that, in the vastness of the universe, there is always more to discover. As the cosmic clock continues to advance, the evolution of this galactic titan will be shaped by forces both predictable and mysterious. While the structure we observe today is vibrant and full of energy, the deeper laws governing the universe ensure that no celestial body remains unchanged. Over unimaginable timescales, this stellar system will transition through different phases, each marking a new chapter in its vast history. The present moment, defined by the ongoing formation of stars, will eventually give way to a quieter era. The great nebulae that now serve as stellar nurseries will slowly disperse, leaving behind only the stars that have already formed. Without a steady influx of cold gas, no new generations will emerge to replace those that burn out. This decline will be gradual at first, barely perceptible over human lifetimes, but over billions of years, the difference will become clear. The galaxy's arms will fade, the glow of massive blue stars will disappear, and only long-lived red dwarfs and cooling remnants will remain. While the visible features of the galaxy change, unseen processes will continue to influence its fate. The dark matter halo surrounding the system will persist as a gravitational scaffold, shaping the movement of its stars even after the loss of its brightest members. Some theories suggest that interactions within dark matter halos could lead to subtle, long-term effects on galactic evolution, possibly altering the way stars orbit or influencing future mergers in ways not yet fully understood. Even as the galaxy settles into a more passive state, the remnants of its former brilliance will still be present. White dwarfs will form a vast population, each a dimming ember of a once luminous star. Neutron stars, the collapsed cores of the most massive stars, will rotate silently, some still emitting faint pulses of radiation. Black holes, formed from the deaths of the heaviest stars, will drift through the system, invisible but ever-present, exerting their gravitational influence. The central supermassive black hole, now dormant or only occasionally active, will remain as the galaxy's silent core. Over time, it may continue to gain mass through slow accretion or by merging with other black holes, should galactic interactions bring new material into its reach. If the system experiences a major merger, this black hole could awaken once more, unleashing powerful jets of energy that briefly reshape its surroundings before fading into darkness again. The long-term fate of the galaxy is also bound to the broader evolution of the universe itself. If cosmic expansion continues at its current accelerating rate, galaxies will drift further apart, severing their connections to the larger structures they once belonged to. Eventually, even the faintest traces of other galaxies will recede beyond the observable horizon, leaving this system alone in an increasingly empty cosmos. Without new interactions to provide fresh material, it will continue its slow transition into darkness. In the deepest future, when trillions of years have passed, even the longest-lived stars will begin to fade. Red dwarfs, which burn their fuel with extreme efficiency, will eventually exhaust their reserves, leaving behind a universe filled only with cooling remnants. The galaxy will become a place of silent white dwarfs, non-rotating neutron stars, and black holes, drifting endlessly through the void. Even these objects, given enough time, may meet their end. White dwarfs will cool to black dwarfs, emitting no heat or light. Black holes, the most enduring structures of all, may slowly evaporate through the slow process of Hawking radiation, vanishing into the vacuum of space. Yet despite this seemingly inevitable decline, the universe remains a place of possibility. If advanced civilizations arise within the galaxy's lifespan, they may develop ways to harness the energy of its remnants, finding new methods of survival long after the stars have faded. Technologies beyond our current imagination may allow life to persist, adapting to the cold, dark universe that will one day emerge. For now, however, this galaxy remains alive, its stars burning brightly, its spiral arms stretching across space, its black hole holding court at the center of a vast and complex system. It is a place of ongoing transformation, where cosmic forces play out on scales both vast and intricate. Every supernova, every drifting planet, every magnetic field tells a story written in the language of the cosmos. As we continue to study it, we are reminded that the universe itself is never static. It is an ever-changing tapestry of matter, energy, and space-time, each moment leading to the next in an infinite sequence of events. This galaxy's journey is far from over, it is simply part of the grand, continuous motion of the cosmos. And as long as there are observers to look toward the stars, its story will continue to unfold, written across the fabric of time itself. The journey of this galaxy through the cosmic expanse continues, an unceasing progression through the vast, uncharted reaches of time. While its present form is defined by swirling arms of stars, luminous nebulae, and a dynamic interplay of stellar forces, the distant future will see it undergo transformations that stretch beyond the scope of current understanding. Each stage in its evolution is part of a grander cycle, where birth, growth, and decay are inextricably linked. Even as the light of new stars fades, the underlying gravitational structures will endure. The stars that once illuminated the galaxy will drift through a steadily dimming sky, bound to their orbits by the unseen mass of dark matter. Over eons, these orbits may shift due to subtle gravitational interactions, causing some stars to migrate outward while others spiral inward toward the central black hole. In some regions, dense stellar remnants may cluster, forming compact systems of white dwarfs, neutron stars, and black holes locked in a slow gravitational dance. While large-scale interactions will become increasingly rare as the universe expands, this does not mean the galaxy will remain entirely isolated from cosmic events. Rogue objects, free-floating planets, interstellar debris, or even intergalactic stars ejected from distant collisions, may pass through its boundaries, altering local dynamics in unexpected ways. Occasionally, binary systems may undergo disruptions, flinging one star outward at immense speeds while the other falls into the depths of a black hole. These rare events will provide brief but dramatic moments in an otherwise long, gradual shift toward equilibrium. At the heart of it all, the central black hole will persist as the galaxy's gravitational anchor, long after its brightest stars have faded. If no further matter is available to feed it, it may remain dormant, a dark monolith at the center of a dying system. Yet in the event of a galactic merger, even in the distant future, it could awaken once more, consuming stellar material and releasing vast amounts of energy in a final display of activity before the universe grows too empty to sustain such processes. On the longest timescales, when even the most enduring stars have faded into obscurity, the galaxy will be reduced to a vast collection of stellar remnants. White dwarfs, once the glowing cores of sun-like stars, will cool until they no longer emit any heat or light. Neutron stars, relics of past supernovae, will persist as silent, invisible spheres of dense matter. Black holes, the ultimate endpoints of stellar collapse, will remain scattered across the galactic remnant, their presence detectable only through their gravitational influence. Yet even black holes are not eternal. The slow process of Hawking radiation, a quantum effect predicted by theoretical physics, will cause them to lose mass over unimaginable timescales. As the final stages of the universe unfold, these black holes will gradually evaporate, releasing their remaining energy into the darkness. Eventually, after a period so long it defies human comprehension, the last traces of what was once a grand and thriving galaxy will dissipate, leaving behind nothing but the vast, empty expanse of space. But even in this apparent finality, the story of the universe itself may not be over. Some theories suggest that new physical processes could emerge in the distant future, leading to the birth of entirely new structures, new galaxies, or even new forms of matter and energy. The eventual fate of the cosmos remains one of the greatest mysteries, one that extends beyond even the long arc of this galaxy's existence. For now, this stellar system remains an active, vibrant participant in the ongoing story of the cosmos. Its stars still shine, its nebulae still swirl with potential, and its future remains unwritten. Whether it eventually fades into isolation, merges with another galactic system, or becomes the cradle of new cosmic phenomena, it is a reminder that the universe is not static, it is an ever-changing expanse of creation, transformation, and mystery. The galaxy's journey, like the universe itself, is one of constant motion. And as long as observers exist to study it, to trace its evolution, and to uncover the forces that shape it, its story will continue, woven into the grand tapestry of existence, a testament to the boundless nature of the cosmos. The passage of time within this galaxy, like that of all cosmic structures, is dictated by forces both seen and unseen. For now, it remains a place of light, energy, and movement, a system still brimming with stellar activity in the subtle interplay of gravity, radiation, and magnetic fields. Yet the deeper laws of physics ensure that change is inevitable. The stars that shine today will one day burn out, their remnants drifting through space, forming the silent foundation of a future where darkness and cold dominate. Even in the near future, on a galactic scale, this system will begin to experience noticeable shifts. The rate of new star formation will decline as available gas reservoirs dwindle, and stellar winds, supernovae, and active galactic feedback continue to expel material into intergalactic space. The most massive stars, those that once defined the brilliance of the galaxy's spiral arms, will be the first to vanish, leaving behind a less dynamic but still evolving stellar population. As the era of new stars comes to a close, the dominant sources of energy within the galaxy will change. While today it is driven by the nuclear fusion of young, luminous stars, in the future, much of its energy output will come from compact remnants, white dwarfs, neutron stars, and black holes. These objects, relics of past stellar generations, will continue to interact in gravitationally complex ways, forming dense stellar clusters where unusual astrophysical phenomena may emerge. With no new material to sustain star formation, the galaxy will enter a state of slow structural decay. The spiral arms, once teeming with brilliant clusters of hot, young stars, will become more diffuse and less distinct. The central regions, dominated by older stars, will gradually take on a more elliptical shape, as stellar orbits become increasingly randomized due to long-term gravitational interactions. If the system does not experience another major merger, it may retain much of its spiral character for an extended period, but eventually, it will lose the energy that sustains its grand structure. The presence of dark matter, though invisible, will continue to shape the motion of stars and stellar remnants. This unseen mass, concentrated in a vast halo extending far beyond the visible edges of the galaxy, will ensure that its overall gravitational integrity remains intact, even as individual stars come and go. Yet as time stretches onward, the exact nature of dark matter's influence remains uncertain. If dark matter interacts with itself or decays over cosmological timescales, it could subtly alter the galaxy's evolution in ways not yet fully understood. Far in the future, black holes will become the dominant gravitational players within the system. The central supermassive black hole, now a relatively quiet presence, may awaken if a late-stage galactic collision provides it with new material to consume. However, if no such event occurs, it will continue to exist in relative dormancy, exerting its pull on the remaining stars and stellar corpses that orbit its dark center. Meanwhile, Smaller black holes, formed from the collapse of once massive stars, will roam the galaxy, occasionally merging and releasing bursts of gravitational waves that ripple through the fabric of spacetime. The next phase in the galaxy's life will be dominated by slow stellar dimming and cooling. The white dwarfs left behind by sun-like stars will take trillions of years to cool to black dwarfs, their faint infrared glow gradually fading into total darkness. The neutron stars, though more stable, will also lose energy over immense timescales, their once powerful magnetic fields dissipating until they become featureless, dense remnants. In the most distant future, when even these last stellar remnants have faded, the galaxy will be reduced to a vast, dark cloud of compact objects. White dwarfs will have long since cooled beyond detectability, neutron stars will have settled into silent motion, and the remaining black holes will be the only significant sources of gravitational influence. The occasional gravitational interactions between these objects may eject some of them into intergalactic space, while others may slowly spiral inward toward the supermassive black hole at the center. Even black holes are not eternal. If the theories of Hawking radiation hold true, over an unimaginable number of years, they will slowly evaporate, emitting minuscule amounts of radiation until they finally vanish. In the final stages, the last remaining structures of the galaxy will disappear entirely, leaving nothing but the expanding void. Yet even in this apparent finality, the larger fate of the universe remains unknown. Some cosmological theories suggest that new physics could emerge at extreme timescales, allowing for the rebirth of matter, the formation of new energy structures, or even the possibility of an entirely new phase of existence. Other models suggest that the universe will continue expanding indefinitely, growing colder and more desolate as entropy reaches its maximum. But for now, this galaxy is still very much alive. It is a place where stars are born and die, where black holes lurk in the shadows, and where gas clouds drift between the stars, waiting to be pulled together into new systems. It is still undergoing change, still writing its story in the language of light and gravity. And as long as there are eyes to observe it, whether human or some other intelligence that may one day rise within its countless stars, its journey through time will remain an inspiration. It is a reminder that the universe is not a static void but an evolving, dynamic entity, filled with forces beyond our comprehension, shaping worlds beyond our reach. This galaxy's tale is far from over. It is but one part of a far greater cosmic narrative, one that stretches across the depths of space and the boundless reaches of time. And as long as the universe itself exists, the echoes of its existence, its transformations, and its mysteries will endure, woven into the grand and infinite fabric of the cosmos. The journey of this galaxy is a testament to the ever-changing nature of the cosmos, where time, gravity, and energy weave an unbroken narrative of transformation. Even as it moves toward a quieter, less dynamic state, the fundamental forces that shaped it continue to operate, ensuring that its evolution, though gradual, will never truly cease. As the last great bursts of star formation fade, the galaxy will settle into a state of equilibrium, where the remaining stars age and cool without the replenishment of new stellar generations. The once vibrant interplay between young blue giants and glowing nebulae will be replaced by an increasing dominance of red and orange stars, those that burn their fuel slowly and persist long after the more massive stars have perished. Over time, even these long-lived dwarfs will begin to disappear, leaving behind a sky populated mostly by stellar remnants, silent echoes of a once thriving system. Though large-scale star formation will have ceased, cosmic interactions will continue on smaller scales. Gravitational encounters between stellar remnants may lead to occasional mergers, where white dwarfs collide to produce faint, short-lived bursts of energy. Some neutron stars, locked in decaying orbits around one another, may spiral inward over the course of eons, unleashing powerful gravitational waves in their final moments before merging into a single, ultradense object. These events, though rare, will be among the last luminous displays in the galaxy's history, marking the remnants of processes that once fueled its brilliance. At the heart of the system, the supermassive black hole will remain the most dominant force, exerting its influence over whatever matter still orbits its deep gravitational well. If no new gas is available for accretion, it will exist in a state of quiet solitude, an immense but invisible presence that once governed the flow of material at the galactic core. However, should future interactions send new objects toward it, whether wandering stars, smaller black holes, or the remnants of galactic mergers, it may still flare to life in brief, final outbursts of radiation before returning to dormancy. Beyond the slow transformations within the galaxy itself, the broader cosmic landscape will undergo equally profound shifts. The expansion of the universe, driven by dark energy, will continue stretching the fabric of space, increasing the distances between galaxies. If current models hold true, this system will one day be so far removed from its nearest neighbors that no light from them will ever reach it again. It will exist in solitude, drifting in an ever-expanding void, separated from any potential sources of new energy or interaction. In this distant future, even the most enduring stars will fade. The red dwarfs, which burn their hydrogen reserves with remarkable efficiency, will eventually deplete their fuel, transitioning into dim, cooling husks. White dwarfs, scattered throughout the galaxy, will continue their slow cooling process, radiating away their last traces of heat until they become black dwarfs, invisible and undetectable, existing only as faint gravitational imprints in the darkness. The galaxy, once a brilliant collection of spiraling stars and nebulae, will become a quiet graveyard of matter, a system of dead stars, black holes, and unseen remnants, orbiting in patterns set long ago but no longer changing. The gravitational pull that once held it together will remain, but without active energy sources, it will simply persist as a vast structure of cold, inactive objects, bound by forces that no longer shape new formations. But even these lingering remnants will not endure forever. If Hawking radiation is correct, then over unimaginable spans of time, even the black holes that dominate the galaxy's final phase will slowly evaporate, radiating away their mass particle by particle until nothing remains. The last trace of structure within this system, indeed, within any system, will be erased as even these cosmic titans fade into nothingness. At this stage, the universe itself may have reached what is theorized as the heat death, a state where entropy has maximized, all available energy has been evenly distributed, and no further work can be done. The last remaining particles will drift aimlessly in a sea of darkness, with no stars to shine, no forces to bind them together, and no structure left to shape the cosmos. And yet, even in this seemingly final state, mysteries remain. Some theories propose that at extreme timescales, new physics may emerge, allowing for the spontaneous formation of quantum fluctuations that could give rise to entirely new structures, perhaps even a new universe. Others suggest that unknown forces, beyond current understanding, could initiate a cosmic rebirth, resetting the universe into a new cycle of expansion, contraction, and formation. For now, however, this galaxy remains a place of light, energy, and motion. It is still home to stars, to planetary systems, and to forces that shape the cosmos on scales both vast and intricate. It is still evolving, still transforming, still existing as part of the grand, ever-unfolding story of the universe. And as long as there are minds to observe it, whether human or some future intelligence that may one day rise within its stars, its journey will not be forgotten. It will stand as a testament to the vastness of time, the relentless power of cosmic forces, and the mystery of existence itself. Even in the face of inevitable entropy, even in the depths of the farthest future, the legacy of this galaxy, its cycles of formation, its celestial dance, its silent end, will remain woven into the fabric of the cosmos, a whisper in the endless symphony of space and time. Even as the inevitable march of entropy dictates the distant fate of this galaxy, its existence, past, present, and future, remains a crucial part of the larger cosmic narrative. While its stars will one day fade, while its spiral arms will dissolve into a formless collection of stellar remnants, and while even its black holes will eventually disappear, it is not a mere passive participant in this grand story. Every collision, every burst of star formation, every gravitational interaction it has ever undergone has contributed to shaping the vast, evolving tapestry of the universe itself. For now, it is still a place of motion, where stars drift along their ancient orbits, where remnants of once massive suns cool in the silence of space, and where the invisible forces of dark matter still hold it together. The fabric of spacetime bends subtly around its remaining black holes, the last gravitational wells marking where brilliant clusters of stars once illuminated the cosmic night. Even as star formation ceases, interactions between stellar remnants will continue. Binary white dwarfs may occasionally merge, igniting in final supernovae that momentarily rekindle some of the brightness lost over eons. Some neutron stars may collide, releasing bursts of gamma radiation that flash across space before vanishing into the abyss. These events will become rarer and rarer as time stretches forward, their light appearing like distant echoes of an era that once flourished. If a cosmic traveler, a future intelligence from a civilization born on one of this galaxy's planets, were to witness its slow transformation, they would see it as a system settling into a quiet, eternal slumber. The intricate balance of forces that once gave rise to its grand structure will dissolve, leaving behind a ghost of what once was. The beautiful, swirling motion of its spiral arms will be nothing but a memory written in the positions of long-cooled stellar remnants, their orbits preserving the shape of the past long after the light has faded. And yet, even in this state of near-total stillness, the galaxy will continue to move. It will drift through the expanding universe, carrying with it the remnants of countless past generations of stars, planets, and possibly even life that once arose in its systems. Every star that has ever shone, every world that has ever formed, every cosmic event that has ever unfolded within its boundaries has left a mark upon the larger fabric of reality. But what lies beyond the end? Some theories suggest that as the expansion of the universe accelerates, structures like this galaxy will become increasingly isolated, eventually disappearing beyond the event horizons of one another. This would mean that, in the deepest future, nothing from the outside universe would be able to reach this lone stellar graveyard. It would exist in complete solitude, no longer connected to the broader cosmic web from which it once drew its material and energy. Yet other possibilities remain open. There are theories that hint at the idea of cosmic rebirth, suggesting that fundamental forces may shift over unimaginable timescales, triggering a new phase of universal evolution. Perhaps the very fabric of space-time will undergo a transformation, giving rise to new structures, new energies, or even entirely new forms of matter. Could something rise from the ashes of this long silent galaxy, reshaping its cold remnants into the seeds of another universe? Or perhaps, if there is intelligence capable of enduring across such timescales, this galaxy may not remain a passive relic of the past but instead a domain of cosmic engineering. If civilizations survive the death of their stars, could they find ways to reignite new suns? Could they harness the gravitational energy of black holes to create new sources of warmth and light? Could they defy the seemingly inevitable fate of entropy, bending the rules of nature to construct a new age of stellar activity? For now, such questions remain beyond our reach. What is certain, however, is that the universe is not a static entity, nor has it ever been. From the moment of its birth, it has been in constant flux, each stage leading into the next, each transition reshaping the fate of galaxies, stars, and worlds. This galaxy's story, though it may seem to end in silence, is not a tragedy. It is a story of cycles, transformations, and endurance. It is a reminder that even in the face of entropy, in the face of an ever-expanding cosmos, there is meaning in the motions of celestial bodies, in the interactions of cosmic forces, in the rise and fall of stellar systems. It is not just a fading structure in an ancient universe, it is a link in a chain that stretches from the distant past into the unknowable future. It is a testament to the grand forces that govern reality, a cosmic echo that will resonate across time. And as long as there are observers, whether human or otherwise, to look toward the stars, to seek understanding, to marvel at the scale of existence, then the story of this galaxy will never truly be over. It will live on in the minds that remember it, in the equations that describe it, and in the unbroken continuum of the universe itself, a whisper in the void, a trace in the infinite, a mark upon eternity. Even in the farthest reaches of time, when the last embers of this galaxy have faded and its structure has dissolved into the silent drift of stellar remnants, its existence will remain woven into the fabric of the universe. The forces that shaped it, the stars that once illuminated its spiral arms, and the events that unfolded within its vast expanse have left an imprint upon reality itself. Though no longer a place of brilliant star clusters and luminous nebulae, it will not be forgotten by the cosmos. The energy that once flowed through its stars has been dispersed, the elements forged in their nuclear furnaces scattered across the void, now part of an unseen legacy stretching far beyond its borders. The gravitational ripples from ancient collisions still echo through space-time, faint but real, inscribed into the very structure of the universe. In a universe where time stretches infinitely forward, the galaxy's past is not erased but absorbed into the grand continuity of existence. Every burst of stellar radiation, every gravitational interaction, every moment of transformation has contributed to shaping the cosmos as it is now, and as it will be in the future. Yet if the universe itself has an ultimate fate, if the expansion continues to accelerate, or if new physics emerges beyond our understanding, then even the idea of permanence may be an illusion. If dark energy persists, this galaxy will be carried ever outward, away from all others, lost in a cold and empty expanse where no new interactions can take place. In such a future, its remnants will continue their endless drift, untouched, unseen, unknowable to anything that might still exist elsewhere. But if the universe is cyclic, if there is a deeper pattern beyond the present expansion, then perhaps this is not the true end. Some theories suggest that the cosmos may one day contract, reversing its expansion and pulling everything back toward a new singularity, a rebirth where all past matter and energy are reshaped into the foundation of a new reality. If such a fate awaits, then this galaxy, though long dissolved, may become part of the material that fuels the birth of new stars, new galaxies, new structures beyond imagining. And even if the cosmos remains in perpetual expansion, with entropy driving it toward darkness, there may yet be unseen forces at play. Perhaps deep in the void, unknown mechanisms could reignite cosmic processes, birthing new structures in ways we cannot yet comprehend. Could remnants of this galaxy, scattered and cold, find new purpose in an epoch where the laws of physics themselves change? If intelligence endures, if civilizations, whether from this galaxy or another, find ways to persist beyond the deaths of their stars, then the knowledge of what once was will not vanish. Records of this galaxy's past may be preserved, its structure mapped, its evolution studied by minds that have transcended ordinary limitations of time and entropy. The image of its grand spiral form, long since unraveled, may still exist in archives that survive beyond stars, beyond black holes, beyond even the last remnants of ordinary matter. For now, this galaxy still turns, still shines, still plays its role in the vast cosmic dance. Its stars are not yet gone, its remnants not yet scattered to the cold depths of time. And as long as it exists, as long as light still escapes from its distant reaches, its presence in the universe remains undeniable. And even when its last light has faded, when its black holes have evaporated, when every particle has drifted into the background radiation of a silent cosmos, its existence will not have been in vain. It has been a part of something far greater, a universe where time does not erase but instead transforms, where energy does not disappear but shifts into new forms, where every celestial body, no matter how fleeting in the grand scale of eternity, contributes to the larger unfolding of reality. This galaxy's story may end in darkness, but it does not end in nothingness. It remains, always, a chapter in the infinite book of the cosmos, its essence forever imprinted upon the grand and unending tapestry of space and time. Even in the depths of an aging universe, where darkness slowly claims what once shone brightly, the essence of this galaxy endures. Its stars may fade, its structures may dissolve, and its energy may disperse into the vastness of space, but its influence, its mark upon the cosmic stage, remains. Every atom, every photon, every gravitational wave that ever emanated from this system is now part of something greater. The elements forged in its stellar cores have traveled far beyond its borders, carried by supernovae, stellar winds, and intergalactic currents to become part of new worlds, new structures, perhaps even new life. Though its own light may no longer shine, the echoes of its existence persist in ways beyond our current comprehension. If there are still observers, beings capable of witnessing the slow unraveling of the cosmos, they may look upon this galaxy not as a relic, but as a monument to the vast interplay of forces that have governed the universe since its birth. To them, it may serve as a record of everything that has come before, a cosmic archive written not in books but in the arrangement of dead stars, in the subtle distortions of spacetime left by its long-past inhabitants. Perhaps, in the farthest reaches of time, intelligence will still endure, outlasting even the stars themselves. If such minds exist, they may develop ways to resist the pull of entropy, to construct new energy sources in the wake of a dying universe. Perhaps they will find remnants of galaxies like this one, gathering their scattered pieces to forge something new in a universe that no longer creates but only erases. Even if no civilization survives, if no mind remains to remember, the fundamental laws of physics dictate that nothing is ever truly lost. Energy changes form, matter disperses, structures dissolve, but the sum total of all that has ever existed continues to shape what will come next. This galaxy, even in its final silence, is part of that greater unfolding, its atoms scattered among the stars, its gravity still shaping the motion of celestial bodies long after its own light has faded. The universe does not forget, not in the way living beings do. The fabric of spacetime itself carries the imprints of everything that has ever been, the traces of every interaction, every force, every transformation. This galaxy, now only a whisper in the void, is woven into that vast, eternal record. And so, its journey does not truly end. It is not merely a structure that rose and fell in the unending expanse of time, but a contributor to something far greater. Whether the universe cycles anew, whether unknown forces bring about a rebirth, or whether entropy carries everything toward a quiet and endless expansion, this galaxy will always have existed. It will always have been part of the cosmic story. Its legacy is written in the light that once traveled across the stars, in the gravitational ripples it sent across space, in the elements it forged that now drift unseen among the ruins of a fading cosmos. It is a memory inscribed upon the infinite, a presence that will never truly vanish. And as long as there are minds, whether now, in the distant future, or in some unknown epoch of reality, to look out into the dark and wonder, then its story, like the universe itself, will never truly be over. Even in the silent vastness of a universe approaching its final, unknowable fate, the existence of this galaxy remains an indelible part of the cosmic record. Though its stars have long since faded, their energy spent, their structures dissolved into the cold drift of intergalactic dust, the very fact that they once shone, that they once gave form to a grand and spiraling structure in the void, ensures that their influence is never truly erased. For now, the universe still expands, still carries the remnants of galaxies like this one outward into the growing abyss. If cosmic acceleration continues unchecked, then the final state of all things may be one of endless separation, an era where the last remaining fragments of matter are so distant from one another that no new structures can form, where even the faintest echoes of past galaxies are stretched across a universe that has grown too vast, too cold, too empty for anything to emerge anew. But even in such a fate, even in a universe that moves toward silence, the memory of this galaxy remains inscribed in the very fabric of spacetime. Every gravitational wave it ever generated, every burst of energy it once released, every particle it sent drifting through the cosmos is now a part of something larger, a universe that has, for all its vastness, been shaped by each of its stars, each of its forces, each of its countless interactions. Perhaps, beyond even the longest timescales we can fathom, something new will arise from what seems to be an ending. Some theories suggest that the very structure of space itself may one day fluctuate, giving rise to new cosmic conditions, new particles, even new universes. Could it be that the energy of long-faded galaxies will one day serve as the seeds of something yet to be born? Could the remnants of matter, scattered across the vast, darkening cosmos, become the building blocks of a new cycle, a new age of light and structure? And if intelligence endures, if there are minds capable of witnessing the slow transformation of the universe into something beyond what we now understand, then they, too, may play a role in ensuring that this galaxy's legacy is not forgotten. Whether through archives stored beyond the limits of time, or through vast cosmic engineering projects that seek to resist entropy itself, there may still be those who hold the knowledge of what came before, who remember the age of galaxies, of stars, of motion and energy. Even if all else fades, even if no one remains to remember, this galaxy's story will have mattered. It was part of the great unfolding of the cosmos, part of the immense and intricate symphony of forces that brought structure from chaos, light from darkness, form from formlessness. It existed, and that alone is enough to secure its place in the eternal record of all that has ever been. For now, its journey continues, its last remnants still drifting, still bound by the gravitational echoes of what it once was. And as long as the universe exists in any form, whether expanding into infinity, collapsing into rebirth, or transforming into something we cannot yet comprehend, this galaxy, and every atom that once belonged to it, will remain a part of the great and endless story of the cosmos. Even in the deep future, when the last remnants of matter drift in a universe grown vast beyond measure, the essence of this galaxy remains woven into the silent fabric of existence. Though no longer a luminous spiral of stars, though its structures have dissolved into the slow tide of entropy, it was, and therefore it is. Its light once traveled across cosmic distances, its gravity once shaped the orbits of countless worlds, and its forces once played their part in the grand symphony of the cosmos. The universe itself is a memory, written not in ink but in the motion of celestial bodies, in the invisible distortions of spacetime left by the passage of stars, in the delicate balance of energy and void. This galaxy, long past its era of brilliance, has left its mark in ways that cannot be undone. The atoms forged in its core, scattered by supernovae billions of years ago, may still drift through space, waiting for a new gravitational well to gather them, to shape them into something yet to be. Perhaps no such rebirth will come. If the universe continues its expansion without bound, if no new structures can form, then matter itself may thin into nothingness, stretched by the relentless pull of dark energy. In such a future, the very idea of a galaxy, of stars and planets, will belong to a past so distant that it can no longer be reconstructed. The distances between remnants will grow so great that no interaction will ever occur again, no light will ever reach another point, no motion will ever again alter the stillness. And yet, even then, the trace of what once was will not be truly lost. The information of this galaxy's existence, of the energy it once radiated, of the forces it once exerted, will remain encoded in the quantum state of reality itself. Some physicists theorize that no information is ever truly destroyed, that even when stars collapse, when matter disintegrates, when black holes evaporate, the fundamental data of their existence persists in some unknown, hidden form. If this is true, then this galaxy, though long gone, will never have been erased. Perhaps, beyond the horizon of time, something will arise to read the final traces of what has been. Perhaps an intelligence beyond our comprehension, existing in a far future state where entropy has slowed, where the last pockets of energy are gathered and used with impossible precision, will find a way to reconstruct the past from its echoes. Perhaps the light of long-dead galaxies will be retrieved, played back in ways we cannot yet conceive, allowing some distant observer to witness the spiral arms once again, to see the stars as they were, to trace the paths of planets that no longer exist. And even if no mind survives to witness it, even if intelligence fades along with the last stars, the fact remains that it was. This galaxy existed, it played its role in the cosmic ballet, it was part of something immense, something unknowable. That alone secures its place in the infinite continuum of reality. The universe is vast beyond understanding, and time stretches forward into the unknowable. Yet within that vastness, every star that has ever shone, every world that has ever formed, every force that has ever acted upon matter has contributed to the larger unfolding of all that is. This galaxy, though now a ghost among the stars, was part of that story. It remains part of that story. And as long as the cosmos endures, its place in that endless, evolving narrative will never be undone. Even in the farthest reaches of eternity, where time itself stretches into the unknowable, the echoes of this galaxy persist. Though its stars have long since faded, though its structure has unraveled into the slow drift of forgotten remnants, it remains inscribed in the very essence of the cosmos. No moment, no force, no celestial motion is ever truly erased. All that has ever been continues to exist in the grand unfolding of reality, woven into the invisible fabric that binds all things together. The final remnants of this galaxy, white dwarfs long turned to black dwarfs, neutron stars reduced to frozen cores of dense matter, and black holes evaporating into the void, will persist until the very last motions of the cosmos come to a halt. If the universe continues to expand indefinitely, these fragments will drift apart, growing more isolated until they are separated by such great distances that even the fundamental forces of nature will no longer bind them together. Each will become a solitary traveler in an ever-darkening sea, moving through a cosmos where no new stars will ever ignite, where no light will ever again break the silence. Yet even in such an ending, the memory of this galaxy is not truly lost. If the nature of information is such that it cannot be destroyed, then every event that has unfolded here, every supernova that once ignited, every world that once formed, every star that once shone, still exists in some unfathomable way. The universe itself, as it once was, may be recoverable, its past encoded in ways beyond our current comprehension. Perhaps there will come a time, billions upon billions of years from now, when something, or someone, reaches into the deep archives of space-time and resurrects the lost light of this galaxy, reconstructing its stars, its planets, its structure from the echoes it has left behind. But even if no such recovery is possible, even if all knowledge is lost to entropy, the fact remains that it was. This galaxy existed. It was part of something vast, something beautiful, something impossible to fully grasp. It was a beacon in the night, a spiral of fire and motion, a place where matter danced in luminous patterns for a brief moment in the infinite. That moment may have passed, but its impact remains, woven into the grand design of the universe, forever a part of the great and infinite tapestry of existence. And so, as long as the cosmos endures, even in the cold and silent twilight of time's final stretch, the presence of this galaxy will never truly vanish. It will remain, an echo in the void, a whisper across eternity, a mark upon the unbroken continuum of all that has ever been. And so, as the universe drifts ever forward into the unknown, this galaxy's journey, though long past its most luminous days, remains part of the grand, unfolding story of the cosmos. It was a place of brilliance, where stars were born, where worlds may have formed, where forces beyond comprehension wove together light and matter into a vast and intricate dance. Though time has carried it toward stillness, though its stars have long since burned their last, its presence is not forgotten, it is etched into the very fabric of existence. For even when the last light has faded, even when the final remnants of matter dissolve into the expanding void, what was will always have been. This galaxy, like all things, played its part in the shaping of the cosmos, and that role, whether small or immense, cannot be undone. It is a whisper across the infinite, a moment of structure in an endless sea of transformation, a brief flicker of ordered motion before the quiet embrace of eternity. And though no mind may remain to remember, though no eye may look upon its spiraling form and marvel at its beauty, its essence will always be woven into the cosmic whole. It is not lost, nor meaningless. It is simply one chapter in the unending book of the universe, a chapter that will forever exist within the vast and unknowable expanse of time. For the universe is not static, nor is it finite in what it holds. As long as existence itself endures, as long as there is space and time in which new things may arise, nothing is ever truly gone. This galaxy's light may have faded, its matter may have scattered, its structure may have dissolved into the cosmic night, but it was, and that is enough. It remains, in echoes, in memories written into the physics of spacetime, in the particles that once formed its stars, now drifting toward futures yet unknown. And as long as the universe itself persists, its story, like all stories written in the fabric of the cosmos, will never truly end. Among the most striking celestial structures ever observed, this nebula stands out due to its nearly perfect geometric shape. Unlike most nebulae, which form through chaotic stellar outflows, its symmetry suggests that powerful, yet precisely controlled forces are shaping its structure. It is located thousands of light-years away, associated with a luminous central star undergoing significant mass loss. The surrounding material forms a complex web of dust and ionized gas, reflecting and scattering radiation in a way that enhances its unusual appearance. Observations in infrared and optical wavelengths reveal that the structure consists of highly organized lobes and equatorial rings. These features suggest the presence of either an intense magnetic field or a binary companion influencing the star's evolution. If a secondary star is present, its gravitational interaction could be sculpting the expanding gas, directing it along preferred axes. This would explain the sharp edges seen in the nebula and the apparent lack of chaotic turbulence that typically characterizes similar objects. The central star is likely in an advanced evolutionary stage, either approaching a transition to a Wolf-Rayet phase or nearing its final collapse. The material ejected into space could be part of a larger process in which layers of stellar atmosphere are shed over time, forming structured nebulae that persist long after the original outburst. The exact mechanism behind the symmetry remains a topic of ongoing study, with hypotheses ranging from episodic eruptions caused by internal instability to a controlled expansion influenced by a strong toroidal magnetic field. Spectroscopic analysis reveals that the nebula is rich in both silicate and carbon-based dust, suggesting complex chemical interactions occurring within its expanding shell. The presence of ionized hydrogen and oxygen lines indicates exposure to intense ultraviolet radiation, which is slowly altering the composition of the surrounding medium. These processes are crucial in enriching the interstellar environment with heavy elements that later contribute to the formation of new generations of stars and planetary systems. The velocity of the expanding gas suggests that the nebula has been evolving for thousands of years, though it is unclear whether it has remained stable over time or if it has undergone significant changes in structure. Some researchers propose that the formation is an optical illusion, where a more cylindrical or bipolar outflow appears squared due to our viewing angle. Others argue that external influences, such as a dense interstellar medium or remnant stellar winds, may be reinforcing the shape by constraining material along specific planes. Advanced telescopes equipped with high-resolution spectrographs are expected to provide more precise data on the velocity distribution of gas and dust. By analyzing how light interacts with different regions, astronomers hope to reconstruct the three-dimensional shape and determine whether the observed symmetry is an inherent property or a temporary phase. If the central star is approaching a supernova event, its surrounding nebula could dramatically brighten as the explosion interacts with the ejected material, similar to what has been observed in other massive star systems. Comparisons to other structured nebulae suggest that mass loss in massive stars follows patterns that are more organized than previously thought. While planetary nebulae often display symmetric forms due to the expansion of shells around dying stars, this particular object exhibits a level of precision that challenges conventional models. If magnetic forces are indeed playing a dominant role, it may suggest that similar structures could exist elsewhere but remain undetected due to their orientation or distance from Earth. Infrared observations have also hinted at the presence of complex organic molecules within the nebula, which could have formed through photochemical reactions triggered by high-energy radiation. Such environments are thought to be crucial in the early stages of planetary system development, as they contribute to the formation of prebiotic compounds that later become part of interstellar dust clouds. Understanding how these materials evolve in different stellar environments provides insight into the chemical diversity of the galaxy. Future research will focus on mapping the precise movement of gas within the nebula and determining whether external factors are influencing its evolution. If a binary companion is confirmed, it could provide further evidence that multiple star systems are a key factor in shaping structured nebulae. Long-term monitoring may reveal subtle shifts in brightness or morphology, indicating ongoing dynamic processes that have yet to be fully understood. If the central star eventually undergoes a supernova, it could transform the surrounding region by sending shockwaves through the nebula, triggering secondary reactions and possibly altering its structure. The resulting supernova remnant would provide valuable data on how pre-existing mass loss affects the aftermath of stellar explosions. If a neutron star or black hole forms at the core, it may interact with the surrounding material in ways that produce additional high-energy emissions, making it a potential source of radio waves or X-ray bursts. The precision of the formation continues to challenge existing astrophysical models, suggesting that either previously unknown mechanisms are at work or that magnetic shaping plays a far greater role in stellar evolution than currently assumed. Upcoming telescopes with adaptive optics and interferometry will provide deeper insights into the processes governing the expansion of ionized gas and the interaction between radiation and dust within the nebula. While its ultimate fate remains uncertain, its significance as an astrophysical case study is undeniable. Whether it is a short-lived phase of stellar evolution or a long-standing feature that will persist for thousands of years, it represents a rare and valuable opportunity to study the forces that shape the most massive stars in the cosmos. The answers it holds could refine our understanding of how stars evolve, how they lose mass, and how they influence the galactic environment over cosmic timescales. The forces responsible for shaping this nebula remain a subject of debate, with multiple mechanisms potentially working in tandem to maintain its strikingly structured form. The presence of a dense circumstellar medium suggests that earlier mass ejection events may have interacted with surrounding material, creating shock fronts that reinforced the observed geometry. If stellar winds or episodic eruptions from the central star were directed by an unseen companion, their effects could have compounded over time, gradually sculpting the nebula into its current configuration. Magnetic fields are another possible factor influencing its development. In some high-energy astrophysical environments, magnetic pressure can guide ionized gas along preferred paths, constraining outflows into collimated jets or symmetric lobes. If this phenomenon is occurring here, it could help explain the sharp definition of the nebula's edges and the near-identical structure on opposite sides of the central star. Observations of other massive stellar remnants have shown that even weak magnetic fields can have a profound impact on outflow dynamics, reinforcing the idea that this nebula's shape may be magnetically driven. The chemical complexity of the surrounding gas adds another layer of intrigue. The discovery of molecular hydrogen and polycyclic aromatic hydrocarbons within the nebula suggests that the region has undergone prolonged exposure to ultraviolet radiation, leading to chemical reactions that produce complex organic compounds. If this material later becomes part of interstellar clouds, it could contribute to the formation of planets or even prebiotic chemistry in future stellar systems. This highlights the role of evolved stars not only as sources of heavy elements but also as potential contributors to the early chemistry of planetary environments. The velocity distribution of ejected material is also a critical factor in understanding the formation of the nebula. If the gas is expanding uniformly, it would suggest that the star has been losing mass gradually over an extended period. However, if velocity gradients are detected, with some regions moving faster than others, it could indicate episodic bursts of energy, possibly linked to a hidden binary companion or internal stellar instability. High-resolution spectroscopic studies will help determine whether the structure has remained stable or if it is actively evolving, with changes in brightness or morphology providing additional clues. Comparisons to other known stellar outflows provide valuable context for interpreting this structure. The similarity to bipolar planetary nebulae, which are often shaped by binary interactions, suggests that the nebula may represent an earlier stage of this process in a much more massive system. If future observations confirm the presence of an orbiting companion, it could provide strong evidence that binarity is a key factor in the formation of highly structured nebulae, challenging existing models of single-star mass loss. The possibility that the central star is approaching a terminal supernova phase adds an additional layer of urgency to ongoing research. If this is a pre-supernova system, then the surrounding nebula may play a crucial role in determining the characteristics of the eventual explosion. A dense circumstellar medium could shape the supernova's light curve, producing an extended afterglow or even influencing the type of remnant that forms. If the core collapse results in a neutron star or a black hole, the interaction between the compact object and the surrounding nebula could generate secondary emissions, including high-energy X-ray or radio bursts. Some researchers propose that this nebula represents a previously unrecognized category of structured stellar outflows, distinct from both planetary nebulae and classical supernova remnants. If so, it could mean that highly organized mass loss occurs in more stars than currently expected but remains undetected in systems with less favorable viewing angles. Advanced three-dimensional modeling, combined with data from next-generation telescopes, will be necessary to determine whether similar formations exist elsewhere in the galaxy. Long-term monitoring will be essential to track any changes in the nebula's structure. If subtle shifts in brightness or gas distribution are detected, it could indicate ongoing mass loss or dynamic interactions within the expanding material. Alternatively, if the nebula remains unchanged over decades of observation, it would suggest that its formation was driven by a past event rather than active processes occurring in the present. Either scenario will provide valuable insights into how massive stars shed their outer layers and how those layers evolve over time. The nebula's role in the broader astrophysical landscape extends beyond its immediate surroundings. If it is indeed an example of a structured pre-supernova outflow, it could help refine predictions for other massive stars nearing the end of their life cycles. Understanding the processes shaping this formation could improve models of how supernovae interact with their environments, potentially leading to better interpretations of historical supernova remnants observed throughout the galaxy. Future research will focus on uncovering the underlying drivers of the nebula's symmetry, whether they be magnetic forces, binary interactions, or unknown stellar dynamics. Upcoming missions and observational campaigns will provide increasingly detailed data, helping to answer fundamental questions about the role of evolved stars in shaping the structure of the interstellar medium. Regardless of what mechanisms are ultimately responsible, the nebula remains a rare and invaluable opportunity to study the complex interplay between stellar evolution, mass loss, and the physical forces that govern the cosmos. As observational techniques continue to improve, new details about this enigmatic formation will likely emerge, shedding light on the precise mechanisms responsible for its near-perfect symmetry. The role of radiation pressure in shaping the expanding gas is an area of active investigation, as intense stellar winds could be driving material outward along well-defined paths. If the star is emitting energy anisotropically, with stronger radiation in specific directions, it could be influencing the way ejected material disperses into space. This could help explain the structured nature of the nebula, particularly if interactions with a surrounding dust disk or magnetic field are reinforcing its geometric appearance. High-energy phenomena may also be contributing to the evolution of this structure. Some researchers suggest that the presence of shock fronts, regions where fast-moving gas collides with slower material, could be shaping the expanding nebula. These interactions create areas of increased density and ionization, altering how light scatters and giving the nebula its distinctive brightness distribution. If these shocks are being driven by periodic stellar outbursts, then the formation could be the result of multiple ejection events over time, each adding to the overall complexity of its structure. Infrared observations continue to provide new insights into the dust and gas composition of the surrounding environment. Data suggests that the dust grains within the nebula are relatively large compared to those found in diffuse interstellar clouds, possibly indicating that they have undergone significant processing due to radiation collisions. If this region is rich in carbon-based compounds, it could support the idea that evolved stars contribute not only to heavy element enrichment but also to the formation of molecular precursors essential for planetary system development. Determining the precise age of the nebula is another critical aspect of ongoing research. By analyzing the expansion velocity of different gas layers, astronomers aim to estimate when the initial mass ejection occurred. If the nebula is relatively young, it could be the result of a recent instability in the central star, whereas an older formation would suggest a more gradual mass loss process over an extended period. This distinction is important in understanding whether this structure is a transient phase that will evolve into a more diffuse remnant or if it represents a long-lived phenomenon sustained by continuous energy input. The potential presence of a binary companion remains a crucial question, as its confirmation would provide a strong explanation for the nebula's ordered structure. If a secondary star is orbiting the central object, its gravitational influence could be directing material into specific flow patterns, producing the observed symmetry. Some models suggest that if a white dwarf, neutron star, or even a black hole is present, accretion-driven outflows could be responsible for the formation's striking shape. Identifying subtle variations in the motion of the primary star or detecting indirect signs of a hidden companion through X-ray or radio emissions may help resolve this mystery. Further study of the polarization of light from the nebula will be useful in determining whether magnetic forces are playing a significant role in its evolution. If light scattering patterns indicate the presence of aligned dust grains, it could suggest that a strong magnetic field expansion of gas. Such align with models of magnetically collimated which have been observed in other environments, including young and active galaxies. The most installation stage of documentix. If it turns out to be a precursor to a more well-known structure, such as a planetary nebula or a supernova remnant, it could provide a unique opportunity to study how these phenomena develop over time. Observing how the nebula changes in the coming years will be crucial in determining its future trajectory, whether it will eventually dissipate into the interstellar medium or continue evolving into a more complex structure. If the central star ultimately undergoes a supernova, the surrounding material could play a key role in shaping the explosion's observable characteristics. The presence of dense circumstellar matter could cause significant interaction between the supernova shockwave and the pre-existing nebula, leading to an unusually bright and prolonged event. If this occurs, it could offer direct observational evidence of how mass loss influences the final stages of massive star evolution. Long-term monitoring with next-generation telescopes will be essential in answering the remaining questions surrounding this extraordinary structure. Instruments capable of resolving fine details in the gas distribution, magnetic field orientation, and spectral properties will provide the data needed to construct a more complete picture of its origins and evolution. If similar objects are identified elsewhere in the galaxy, it may indicate that these types of structured outflows are more common than currently believed, potentially leading to a re-evaluation of existing models of stellar mass loss. Regardless of its ultimate fate, this nebula remains one of the most visually striking and scientifically valuable examples of how complex forces interact in the late stages of stellar evolution. Whether shaped by binary dynamics, magnetic fields, episodic outbursts, or a combination of multiple factors, its existence challenges conventional astrophysical theories and offers an unparalleled opportunity to study the intricate processes governing massive stars. Future observations will undoubtedly bring new discoveries, deepening our understanding of how these cosmic structures form, persist, and eventually transform into the next generation of celestial phenomena. As observations continue to refine our understanding of this extraordinary formation, the interplay between multiple astrophysical forces becomes increasingly apparent. The near-perfect symmetry suggests that a finely tuned combination of stellar winds, radiation pressure, gravitational dynamics, and possibly magnetic confinement is at work. Each of these factors contributes to shaping the expanding shell of gas and dust, maintaining its structural integrity over time. Whether this level of organization is an inherent property of certain types of stellar outflows or a rare coincidence of conditions remains an open question. Infrared spectroscopy has revealed variations in the temperature and density of different regions within the nebula, indicating that it is not a uniform shell but rather a complex, layered structure. This suggests that multiple ejection events may have occurred at different times, each adding a new component to the overall formation. If past eruptions have been episodic, possibly regulated by internal instabilities in the central star or interactions with an orbiting companion, the nebula could be an evolving record of its progenitor's mass loss history. The detection of specific ionized elements in the surrounding gas suggests that high-energy radiation from the central star is actively altering its chemical composition. Regions exposed to the most intense ultraviolet and X-ray flux exhibit signs of ionization-driven molecular dissociation, while more shielded areas retain heavier molecules and dust grains. This dynamic environment provides insights into how massive stars influence their surroundings, gradually enriching the interstellar medium with elements forged in their interiors. One of the primary challenges in understanding the nature of this structure is determining whether its symmetry is a transient feature or a long-term characteristic. If it is the result of a recent outburst, it may slowly degrade over time as the expanding material interacts with external forces. On the other hand, if it is stabilized by ongoing processes, such as a sustained mass flow or a persistent magnetic field, its geometry may remain largely unchanged for thousands of years. Tracking subtle shifts in the nebula's brightness and morphology over successive observational periods will be essential in distinguishing between these possibilities. Comparisons to other known examples of structured nebulae suggest that ordered mass ejections are more common than previously assumed. However, the degree of symmetry observed here is exceptionally rare, indicating that specific conditions